by the Department of Chemistry under the DBT Star College status. We, on behalf of Department of Chemistry and the KVP College Vashi, we welcome you, warm welcome you in this program. So I will request first our Honorable Principal Ma'am.
Day and the Enrico Fermi Memorial Lectures in collaboration with Navi Mumbai Science Foundation. We are extremely thankful to the foundation and especially Dr. M. Bhagwat for continuously collaborating with us in celebrating this very wonderful and unique occasion. I'm saying it's unique because very rarely all over the world you will see it is being celebrated in such a big way.
Please everybody mute.
I think
Everybody
my
mute
voice
their
is
mic.
echoing.
Everybody, all of you, please mute your microphone.
Very quickly, I will brief you about our Sanstha and college. Um, this college, Karmaveer Bhaurao Patil College, Vashi, belongs to Rayat Shikshan Sanstha Satara, which is 101-year-old educational institute, which is largest in Asia. We are very proud to be a part of such illustrious Sanstha. And the Sanstha has around 738 branches, out of which 42 are colleges. And there are
Professor,
6
get your
autonomous
mic
colleges,
quiet.
and we are one of
We
them.
get a lot of
We are
echo.
located in Vashi, Sector 15A. It is a first autonomous college of Navi Mumbai, accredited by NAC with A plus grade and 3.53 CGPA. Our college provides education in all the 3 faculties, that is arts, commerce, and science. It has 19 different departments, and we run around 28 different programs, including in 4 departments, we have PhD as well. And this college has received a lot of honors and some important grants. This college is recognized by Department of Biotechnology, Government of India as a star status college. For 4 years, we were in star college scheme, and looking at the good work we did, the star status is awarded by DBT. We have received DST Feast grant. Also, last year we received a grant of around 5 crores by RUSA, that is Rashtriya Uchchatar Shiksha Abhiyan MHRD, under component 8, which is given for some few select autonomous colleges in the country. And with a strong staff of around more than 200 and the students around 8,000, we are constantly making efforts to excel in the field of education. I am very thankful to all our departments and especially today Department of Chemistry for taking lead and organizing such wonderful uh, event, which has started already from last week in the form of essay competitions, knowledge tests, etc. And there was enormous response to both these activities, details of which will be told soon by the head of the department, Professor Gaikwad. And once again, I thank Navi Mumbai Science Federation for giving us an opportunity every year to organize this event. Thank you so much.
Thank you very much, ma'am. We are very much proud of having part of the Red Shikshan Samstha, the Asia's biggest educational institute. So thank you for such a wonderful the words and the inspiration talk. Thank you very much, ma'am. Now I am going to give a brief about my department. Respected dignitaries, today's chief guest, Honorable Jagtap Sir, IIT Bombay. Invited speaker, Honorable Dr. Madhav Malia, Dr. Sonali Sir, Dr. Murali, our dynamic and multitasking principal of our college, Honorable Dr. Shubhada Naik Ma'am, Vice Principals, Organizing Secretary of this event, Dr. Bhaurao Sir, other dignitaries, my colleagues, and finally, we target the audience, that is the young the students of our prestigious Rayat Shikshan Sanstha's 43 colleges and the members from the general public. A very good morning to all of you. It is indeed my pleasure to give you an overview of the activities of my chemistry department. Among the various departments, chemistry department is the biggest department of the science faculty. The department offers courses from 11th standard to the PhD. At the MSc level, we have 3 specializations like organic chemistry, inorganic chemistry, and the analytical chemistry. The department also offers MSc by research course. The department has 8 well-equipped laboratories to facilitate teaching learning process. The department is IT enabled with good configuration computers with broadband connectivity and LCD projectors. Separate lecture recording facilities also there. The department has well-furnished and equipped laboratories. The current faculty members have the diverse research interest in the chemistry. All the members are actively engaged in the research activities. Our department is established in 1979. Total 9 patents published by faculty members and the students. DBT Star College status, that is Government of India. Department received 60 lakhs of the grant. It offers UG to PG up to PhD courses. 20 well-experienced faculty members that working under the department. Large number of research papers published in UGC care listed journals as well as in the international journals, having best impact factor and excellent citation index also. Well equipped, the separate instrumentation lab for UG, PG, PhD students. Departmental library also there. Placement services we provide to UG to PG students. Warm and stimulation, a learning environment to ensure overall development of the students. Introspection, came club to the nature leadership and ensure the accountability for the self-development. Special short-term course on the quality control and quality assurance. Industrial pharmacy, RUSA-based course run by the department. Support of our placement, good research projects and publication. Student publication supported by the department. Avishkar championship at the zonal level conducted by the University of Mumbai, and various innovative the practical demonstration we conduct. With this brief, the introduction of my department, I will conclude my speech and I will give the mic towards Honorable Chairman of the NMSF, Dr. Bhagwat sir. Thank you very much. Bhagwat sir, over to you. Bhagwat sir.
Mic has to be unmuted.
Unmute kara. Bhagwat sir, mic unmute kara. Hello. Bhagwat sir. Hello.
Bhagwat sir.
Yeah.
Unmute kara mic. Yes.
Is it okay?
Okay. Yes.
Yeah. Good morning. Respected dignitaries. That is today's chief guest, Dr. Jagtap sir. Invited speakers, Dr. Madhav Malia, Dr. Sonali, and Dr. Murali. Principal of the college, Dr. Shubhada Naik Madam, Vice Principal and Head of the Department of Chemistry, Dr. Gaikwad sir, Organizing Secretary of this event, Dr. Vadva sir, other dignitaries, that is my colleagues at Navi Mumbai Science Foundation, staff members of this college, and finally the target audience, the young students of 43 colleges of Rayat Shikshan Sanstha and members of general public. A very good morning once again to one and all on this pleasant, mild winter day. It is indeed my pleasure to give you an overview of the activities of Navi Mumbai Science Foundation first, and then say a few words about today's event. Navi Mumbai Science Foundation is a science-led NGO. Is a science-led in India, which was established in the year 2007. It is dedicated to development of scientific temperament in the society in general and in student community in particular. From this point of view, it plans scientific activities that mostly involve students in the age group of 10 to 17 years, which are the most formative years in the life of any individual. In this context, I wish to state that Navi Mumbai Science Foundation has been privileged to have a few dedicated scientists from Bhabha Atomic Research Center in its fold, who willingly interact with young students on a regular basis. The focal point of these interactions is dealing with one, that part of science which lies beyond the four walls of the classroom, and two, that which is hidden in between the lines of the textbooks. The excellent student response to this approach has emboldened Navi Mumbai Science Foundation to have a vision of its own, which is purely pupil-centric and focuses on hands-on experience in science. As a result, the number of scientific activities being organized by this NGO has been constantly growing, from 3 initially to a dozen now, the most challenging amongst them being an essay competition on the topic Nurturing Talent for Nobel Laureatism for students of Standard 9 and 10. Coming to this day's event, that is World Nuclear Energy Day, may I inform the audience that our journey with this college on this path started 7 years ago, and today we are celebrating it for the 8th time. In this context, it will be quite relevant to ponder over the fact that why at all we have undertaken to celebrate World Nuclear Energy Day. We are aware that all the activities around us are based on consumption of energy in one form or the other. Further, it has been established that the quality of life and per capita energy consumption are intimately interlinked. A real change in the pattern of life then became visible only after mass production of energy became possible. It all started happening about 2 centuries back when plentiful energy, especially in the form of electricity, became a reality. Other factors that came in the picture were higher content of energy per unit mass of fuel and cleanliness associated with the production process. It is here that nuclear fission surpassed the other sources such as coal, oil, and natural gas. With India's low per capita consumption and a rapidly growing population, enhanced electricity generation assumed utmost priority. Amongst the various sources considered, nuclear energy appeared to be a viable option. A sincere beginning was accordingly made. However, a lot started appearing against it in the print and other media. It was therefore high time to sort out truth from opinions and project a real picture before the enlightened society. Taking note of this requirement, Navi Mumbai Science Foundation started looking for a suitable occasion where views and opinions could be discussed threadbare. In this endeavor, Navi Mumbai Science Foundation noted that Though controlled release of energy in nuclear reactor was demonstrated for the first time on December 2, 1942 by the scientist Enrico Fermi and his team, no special significance was attached to this day. Navi Mumbai Science Foundation therefore decided in the year 2013 to to introduce this day as World Nuclear Energy Day. This idea was the first of its kind anywhere in the world, and credit must be given to the organizers. It was also decided to organize Enrico Fermi Memorial Lecture on this day in honor of that great scientist. In the recent years, however, the scope of this memorial lecture has been widened to include several other related topics, primarily to give the students a broader view of emerging areas of research in basic sciences. Today's event is noteworthy as it is taking place under the shadow of corona pandemic. The audience is scattered all over the place and looking after their own personal comforts. I am personally grateful to all of them. Finally, I thank you all for lending me your ears for a while and wish you a fruitful journey through the day. Thanks once again. Now, before going off the screen, I have a pleasant duty to perform, that is, of introducing our chief guest, Professor B.N. Jagdap, to this August gathering. Professor Jagtap is presently a senior member. Some disturbance. Professor Jagtap is presently a senior faculty member in the Department of Physics, Indian Institute of Technology, Bombay. Until 2016, he served as a distinguished scientist and director, chemistry group at Bhaurao Atomic Research Center, Mumbai. His research interests include laser physics and technology, quantum optics, laser cooled atoms, and conversion of basic research to societal and industrial technology. The last one being the most important contribution, as it is somewhat uncommon amongst the leading scientists in India. He is a recipient of several awards and honors. However, I will mention only a few of them here, which stand out in the Indian context. Amongst the awards, Homi Baba Award for Science and Technology. Second, His Highness Jagadguru Shankaracharya Award for National Eminence. Third, Platinum Jubilee Lecture Award of Indian Science Congress. And fourth, Senior Visiting Fellow Award of Center of Chemical Physics in Canada. Amongst the honors, he was elected President of Physical Sciences Section of 99th Indian Science Congress. Two, President of Indian Society for Atomic and Molecular Physics. And three, President of Laser and Spectroscopy Society of India. He also sorry. Yes, sir. Just a minute. I'll call you. Sorry. Amongst the honors, he was elected President of Physical Society Section of 99th Indian Science Congress. Two, President of Indian Society for Atomic and Molecular Physics. And three, President of Laser Spectroscopy Society of India. He's also served as editor of Indian Nuclear Society News for over 10 years. Currently, he is associated with a number of councils and committees on higher education. He has authored a book titled Re-Engineering Higher Education in Maharashtra, published in the year 2019. With this humble introduction, may I now request our dear guest to take charge of the floor. Today, the audience is going to witness a two-in-one personality, a scientist and a literate here together. In the talk, The Return of the Low Energy Photons. Dr. Jagdap, please.
Professor Bhagwat, for a very kind introduction. Let me start presenting my slides and then I need permission to share my screen.
Yes, sir. Share. Please, sir.
Yeah. It's still saying that I can't share my screen. No, I don't have permission.
Permission, sir. There is no anybody is going to share screen.
But I need permission. What it is showing is you must grant permission in order to share.
But the option is not over here. There is no option that shown on my screen.
Well, I can't do anything. See, if I can't share my screen.
Sir, permission, there is no meeting details once again.
Professor Bagu, the permission is only from your browser. You have to give the permission to the browser to access the presentation.
Oh no, I thought. Sorry. Can you do it for me? Look.
It is a permission in your computer. So you what browser are you using, sir?
Oh, I have.
Firefox maybe. Yeah. Firefox, then I can immediately. When it is asking for permission, you say allow.
From my side, the permission is already granted. Yes, आ गया. So the screen is started. The screen is showing, sir. So screen is visible now. Yes. It is visible, sir. Audio is not there, sir.
He has to unmute.
It is already unmuted, sir.
Oh yes, he can talk now. No, we are not hearing.
We are not hearing. So there will be a permission. If there is a MacBook,
there is a
permission.
he has to give the permission. Yeah, he's giving.
Permission to the MacBook.
He's giving. Yes.
Yes.
He was talking nicely.
He's talking, but There is no permission for microphone from sir's computer.
No, he gave the permission for microphone. Allow audio and video. It is appearing.
That is autoplay. That permission is given, I think.
So that autoplay permission should be denied.
Permission should be denied.
हाँ लगता है वैसा ही. Sir, can you send your presentation to me? Then I will share. Hello, sir. Can you send your presentation to me? I will share then.
So why not you try to rejoin? Hello, sir.
Hello, भागवत sir.
बोला.
सरांना म्हणा तुमचं प्रेझेंटेशन जर मला पाठवलं तर मी शेअर करतो.
I don't know whether he has put in that form. I'll give him a ring.
जरा कॉल करा.
Yes.
सर वॉइस त्याच्यामधून
आम्ही भागवत बोलतोय ते तुमचं
सर ते पाठवू शकतो पण त्याला काही अर्थ नाही. नेक्स्ट स्लाइड एव्हरी 5 मिनिट्स व्हायचं.
हो. अच्छा.
आज
परत रिजॉईन व्हा म्हणा मग. नाही आता आवाज येतोय. हॅलो सर. भागवत सर. हॅलो.
माइक म्यूट केलंय.
भागवत सर अनम्यूट करा.
केला बोला. केला
त्यांचा आता आवाज आलेला आम्हाला.
आवाज आला.
हा आलेला बोललेलं ते आता ऐकायला आलं.
ते माझ्या व्हॉट्सअपवर बोलले.
नाही इकडे ऐकलं ना आम्ही पण.
ओके. सो हाऊ डू वी मॅनेज? Current. According to him, he's taking almost 5 lectures per week. And there is no difficulty. So today, he needs permission from your end.
नाही माझ्याकडून सगळ्या परमिशन दिलेल्या आहेत. No.
Now somewhere that chain of command is broken.
नाही ऑल परमिशन दिलेले आहेत इथून सगळ्या.
How do we proceed then?
Sir, please ask him to rejoin.
रिजॉईन केलं तर
Jagtap sir, can you rejoin? Disconnect and rejoin. आता आवाज येतोय सर.
Okay, can you hear me now?
Yes.
Okay, but let me see after this the part.
I'll just talk to Dr. Gaikawad sir and get back to you, sir.
Jagtap sir, your presentation and audio is visible, audible and visible.
No, I'm hearing you through my mobile.
हॅलो भागवत सर, तुमचा व्हॉट्सअप कॉल चालू ठेवा, सरांचा आवाज येतो.
अच्छा.
Sir, please tell Jagtap sir to put earphone.
ते हॅलो जगताप सर ते सगळ्यांना इयरफोन लावायला सांगितले आणि मी माझा मोबाईल ऑन ठेवतो. I don't know how with that this will help.
Oh no, let me try out something.
Okay.
आवाज येतोय सर.
हा ते कसं कोण चेंज करेल? नाही ते काय म्हणाले मला हॅलो, दर आठवड्याला ते 4-5 लेक्चर्स IIT घेत असतात. त्यांना त्यांच्या एंडला काहीच करावं लागत नाही एक्सेप्ट जॉईनिंग. सर, त्यामुळे त्यांना कल्पना नाही काय करायचंय त्याच्या एंडला. असेल ती अच्छा अच्छा. जेव्हा प्रेझेंट करतो ना आपण त्यावेळी काय करतात की राईट साईडला मोबाईलच्या सेटिंग असतात. त्यामुळे एंट्री नंतर माईक सेटिंग आणि व्हिडिओ सेटिंग असं 2 सेटिंग येतात. ऍट दॅट टाइम माईक सेटिंगला सेम केलं तुम्ही तर त्याबरोबर व्हॉइस येतो प्रेझेंट करताना. अच्छा, बघतो मी सांगून बघतो, कारण त्यांना ते किती त्याची कल्पना आहे मला सांगता नाही येणार. ओके ओके.
सारंग सर. सारंग सर.
हॅलो,
तू जरा एक स्क्रीन शेअर करून बोल बघू, जरा टेस्ट करूया.
ओके ओके ओके, जस्ट अ बिट. I think I'm
the setting is okay now. From this side, all settings are okay.
when you enter the setting, that's the service. In this, you have to change the microphone setting.
Fine. You don't worry. Try this. Can you remove your presentation? I'll start presenting. Now, can you hear me?
Yes.
Okay. See, I had to go through some other route. Okay. Thank you very much. And I'm indeed happy to give this lecture in Karmaveer, Bhaurao, Patil College, Vashi, and I have great there is a lot of echo.
Professor Gaikwad, please, sir, mute your mic. Professor Gaikwad should mute his mic.
Well, I have a great respect for Karmaveer Bhaurao Patil as a person, a great man, an educationist, and a social reformer, and a true disciple of Mahatma Jyotiba Phule. So I'm really honored to be here. And thank you very much for bestowing this honor of delivering Enrico Fermi Memorial Lecture to you. And I accept this with all my humility. On this World Nuclear Day, I greet you, and let's make it a resolve that we make this country energy self-sufficient. I have selected a topic which is very different from the usual talks in the nuclear energy programs, but I will anyway end up in coming to the same end, that is the nuclear energy and its various applications. But let us begin this lecture by saluting that great man, the Enrico Fermi. And he was one scientist, was a theoretician and experimentalist rolled in one. And here you can see his achievements in science. In 1924, he discovered the statistics for particles obeying Pauli exclusion principle, and all these half integral spin particles, we call them as fermions. In 1934, he gave the theory for beta decay, a puzzling problem at that particular time. 1934 to 36, he worked on the nuclear transmutation by neutron bombardment, and by 1938, Fermi was the best neutron physicist around the world. And in 1938, he received the Nobel Prize for Physics for his work on nuclear transmutation using slow neutrons. And there is another side of Enrico Fermi, and that is what we are celebrating today, the architect of the nuclear age. From 1939 to 1945, he played a key role in the Manhattan Project, that is to develop the nuclear weapon and the nuclear reactor. After Manhattan Project, he took on to his research on particle physics, worked on pions and muons, and also on the cosmic rays. Well, friends, there are lots of stories about Fermi, and since I'm talking to the teachers of a college, I would like to impress upon certain ideas of Fermi, which are really truly useful in the education. But let me give you the story behind it. The world's first nuclear explosion, the Trinity, happened on July 16, 1945. And Enrico Fermi, who was about 9 kilometers from the epicenter of that explosion, estimated the strength of that nuclear explosion by doing a very simple experiment. What he did was that he dropped bits of papers from about 2 meters height, and when the shock wave came to Fermi, the papers were displaced by about 2.5 meters. And from this observation, he estimated the strength of the explosion to be about 10 kilotons of TNT. And later on, when all the experimental data was analyzed, well, the figure was 18 kilotons. So close by doing a simple experiment. And this idea that you can estimate anything with justified guesses is now called as a Fermi estimates. It's a back of the envelope calculation, but which works. And the idea behind the Fermi estimate is to make justified guesses to obtain good approximate results with little or no data at your disposal. Now, there are lots of Fermi estimates available, discussions is on, and they're all on science. But look, this great man could connect with anything and give an estimate. And just for the students attending this, how did Fermi do one example? Now, Fermi was asked that, well, you can estimate the scientific things, numbers and all that, but you tell me how many piano tuners are there in the city of Chicago? And in about few minutes, Fermi comes up with a number about 25 to 30. And people, when they looked at the yellow pages, they found that this number was right. How did Fermi arrive at these numbers? And this is the scheme that he uses, the justified guesses. And I'll step by step explain to you, and I'll tell you why I am doing it. The population of Chicago that time was 30 lakhs, the average 4 per family. So number of families becomes 7.5 lakhs. Average 1/3 families have piano. You can look around your friends and see how many have piano and arrive at a figure 1/3. So the number of pianos in the Chicago is 2.5 lakhs. Each piano requires tuning every 10 years. So number of pianos to be tuned per year is 25,000. And if there is a tuner, he tunes 4 pianos per day and works for 250 days per year, then one person can tune 1,000 pianos. And therefore, the number of piano tuners in the city of Chicago are 25. Look at the way he uses the logic, gives the big numbers, and arrives at a number which is close to the reality. And this is the teaching strategy. For creative learners, the Fermi estimation is a strategy for teaching. And what it tells, I mean, since you are all in education, our students need to know the dimensional analysis. They need to know the order of magnitude estimates. They must have a feel for numbers. If you ask students that, well, the atmosphere, the mass of the atmosphere is 10 to the power 21 kg, does it make any sense to him? There's a feel for numbers and connecting seemingly unrelated facts to arrive at something which is tangible. And this all goes beyond the usual formula based learning, which is so much prevalent in Indian education system. You give V is equal to U into T plus half a T square, and the student puts in the numbers and gets some value. It doesn't have the feel for numbers. And now that we are talking about the new national education policy for the creative thinking, inculcate creative thinking, the power of analysis, and all that, the schools in West have been using the Fermi estimates as a teaching strategies, whereas we have not paid attention to it to bring that creativity and the idea of numbers. And as Lord Kelvin said, that anything which cannot be expressed in numbers is not science, and therefore we need to put in this. But then some of you may ask, why do Fermi estimates work? Well, the law of probability dictates that the error in the reasonably assumed values give overall cancellation. So it works very well. So you ask your students, not a scientific question, but ask how many bald people are there in India? Well, the student should be in a position to estimate it. The population of India is 130 crores. Half of them are women, and therefore 65 crore men can become bald. And every day we hear 65% of our population is below 35 years, two-third population below 35 years. And anybody who is above 35 has a chance to become bald. So two-third, one-third people can become bald. So 65 by 3 becomes 22 crores. And then you look around and see in your neighborhood how many people really get bald when they grow beyond 35. It comes out to be about 10%. So you hit the figure 2.2 crores. This is the way the estimation, this is what there are scientific questions also. What is the mass of the oceans? Well, the student can take the radius of the earth and the depth of the seas and arrive at a number, and then he should be in a position to understand whether what the number he gets is close to the order of magnitude compared to the real number. And this is what needs to be done to our younger generation. Now, today we are celebrating the birth of nuclear energy. And the first reactor that was made critical was called the Chicago Pile 1, where the self sustaining nuclear chain reaction was initiated on December 2, 1942. And this is a picture of the Chicago Pile. And I don't need to discuss the physics behind the sustaining chain nuclear chain reaction, but I'll bring to you the words of Enrico Fermi himself. The fundamental point in fabricating a chain reacting machine is, of course, to see to it that each fission produces a certain number of neutrons, and some of those neutrons induce fission further. And then this is a picture of that, another picture of the Chicago Pile. And just to revive the history, it had 40,000 graphite blocks, and they were kept in 25 feet wide by 12 feet tall wooden box. Mind my word, wooden box. And inside half of these blocks were small start anything in our country? Answer is no. We don't respect our history. We don't respect our scientific history. I can also tell you that I keep giving a lot of talks on the ancient Indian science, and I make it a point to tell my audience that, look, there was a chemist called Nagarjuna, and we do not know how to place him, where to place him, whether he was 200 AD or 700, 800 AD. 600 years, we just cannot place a person and his work, Rasaratnakara. This is our attitude towards our own history. And this is what the younger generation must change. And this event was marked, and there is in University of Chicago, there's a plaque there on December 2, 1942. Man achieved here the first self-sustaining chain reaction and thereby initiated the controlled release of nuclear energy. Well, Chicago Pile worked for a couple of hours, and the radiation and heat was very high. So it was shut down for some time, and then necessary equipments for the heat removal and radioactivity were taken, and for a couple, one year or so it worked, and then it gave rise to the Chicago Pile 2, which was placed outside the city of Chicago. But this happened to be the birth of nuclear energy. And in the subsequent years, the nuclear energy grew in leaps and bounds. In the initial period of nuclear energy, the word pile was used, like the Chicago pile. But later on, this made way for the reactor. So we started calling it as a reactor. And now, with this small brief on the importance of the day, I come to the topic of my discussion, the return of the low energy photons. All of you know the electromagnetic spectrum. It goes from high energy side, from gamma ray, then X-ray, then ultraviolet, then visible, and then infrared and microwave photons, so on and so forth. The low energy photons are these photons here, and this is what I will be concentrating on. Their energy is about an EV, electron volt. As compared to the gamma ray photon, they've got energies of MeVs, 10 to the power 6 times the energy of these photons. And these are the photons which I'm going to discuss and see how they were fighting for their survival in a poetic sense, and how they have turned the table in recent years. Now, the sunlight has been the source of low energy photons. You can see the solar spectrum here, the spectral irradiance versus wavelength, and you see it peaks around 500 nanometers or somewhere around that. And that is where this is the green, yellow-green region, and that is of very important to us. Now, the sunlight and the life on this planet have an interesting relationship. 4 billion years ago, the sun and solar system was formed, and early life on this earth came 3 billion years ago. So for 3 billion years, this life on this earth has been living with these low energy photons. We came into existence only 1 million years ago, the first man, Homo erectus, and about 500,000 years ago, the early man, and then we evolved. But the important issue is this low energy photon, this life has adjusted so well. And I'll just bring 2 instances, and these are all the curiosities in sciences which the younger generation should look at. If you look at the spectral sensitivity for the human vision, it peaks exactly where the solar spectrum peaks. That's around 500 odd nanometers. So our eye got adopted to this low energy photon, the photons coming from the sun. What about the plant kingdom? If you look at the rate of photosynthesis in the plants, very interestingly, where is the peak of the solar radiation, there is a dip in the rate of photosynthesis. And that is why the green light, the plants reflect, and therefore you see them green. Now, what is that happening here? That the plants do not absorb the photons which are at the peak of the solar spectrum. Well, this particular thing attracted attention for a lot of years, and only around 2014 and 2016, there is some definitive proof that has come for this. And the idea here is that the whole process of photosynthesis involves electron transfer. And if the plants absorb the green light, which is the largest component in the solar spectrum, the number of electrons can grow and the whole system can become unstable. And therefore, the plants do not take the green light, they reflect it. The theory of evolution tells us that it is not the efficiency that matters for the evolution, it is the stability that matters. And to make the plant photosynthesis stable, the plants reject green light and they do photosynthesis with the other light. And this particular principle of evolution also we see in ourselves. If efficiency was a criteria for evolution, then we would have developed not feet but the wheels. But if there were wheels, then the whole system would become unstable. So this is the principle of evolution that we need to look at. The sunlight happened to be the source of low energy photon, as we said, and until 1700 AD, the sunlight was the primary source of energy all over the world. The firewood, which is all created by the sunlight, the people used to sell through the oceans by the winds which were generated because of the heating of the ocean surface by sun. And all that was only the sunlight was the only source. Only towards the end of 17th century, when in England, the firewood became expensive, people turned to coal. Looking at the sunlight, in the later years, mankind invented light sources. And it invented the light sources which were akin to the sunlight. So you have the halogen lamp, you have the mercury lamp. You want to have that exactly very similar to what sunlight is. Again, the source of low energy. And right from the beginning, these photons, the mankind was curious. What is it all about? And it gave rise to very, very fundamental concepts on which the modern science is built. All those experiments were done with this tiny 1 electron or 1.5 electron photons. And this is just for the students to give you how our perception about light has laid the foundations of modern physics. Well, we know Newton's work that white light is composed of 7 colors. And then Huygens comes up and says that light is a wave, and Newton says light is a particle. And Fresnel, after 100 years, says no, light is a wave. In 1853, Armstrong found those lines of hydrogen in the visible region. 1860, the wave theory got a burst. Maxwell's theory could explain it. And the Hertz experiment showed that the light is an electromagnetic wave. However, at the turn of the last century, Max Planck on the black body spectrum said the light is a particle. It's a quanta. And this idea was further consolidated by Einstein in his photoelectric effect. The light is a particle. From Armstrong's experiment in 1913, Bohr developed the quantum theory of light, quantum theory of hydrogen atom. And from 1905 to 1924, people were discussing the wave-particle duality of light. Light can act as a wave as well as particle. And it depends on what experiment are you doing to see the nature of light. And enthused by this, in 1924, de Broglie proposed the wave-particle dualism for the particles themselves. If light can act like a particle, then the particles also can act like wave. And then the rest is the history. From 1925 to 26, the quantum theory, which is the fundamental theory of physics, the sciences, took shape, with Schrödinger and Heisenberg contributing to most of it. And then, while the low energy photon was ruling the roost, well, the gamma ray photon entered in a very interesting way. The gamma ray photon entered with its cousins alpha and beta rays, and their origin is in the nuclear processes, either in the fission were not known earlier, but alpha and gamma decay of the radioactive isotopes. And lot many scientists contributed to this from 1896 to 1911. The alpha beta rays were discovered by Becquerel, the radioactivity by Curie. The gamma ray was discovered by Villani, the polonium, radium, and the transmutation due to the radioactivity. The important milestone was the discovery of neutrons by Chadwick in 1932. And in 1938 to 39, the nuclear fission as an idea it took place. Otto Hahn, Fritz Strassmann, Lisa Meitner, Otto Frisch, the great scientists. And all that was put in the right format in the Manhattan Project, what we discussed a little earlier, 1939 to 1945. And from then, the gamma ray started, and its cousins, they started entering every walk of our life. And there are some pictures which you keep seeing in the atomic energy programs that, well, these are used in the health for diagnostics, therapy, sterilization, teletherapy, bronchotherapy, brain imaging, and all that. They're useful in nuclear agriculture, creating new varieties of seeds that have high yields and high resistance to pests as well as the abiotic stresses. And lots of such varieties have been developed. The radiation processing of foods for sprout inhibition, eliminating microbial contamination, enhancing shelf life, quarantine treatment, disinfection, the radiation plays an important role. Also in the industry, the radiography, radiation polymerization, and also in a very complex structure of the chemical reactor, you want to track the flow, then you can use the radioactive isotopes. Water and municipal waste management, you can use radio tracers for groundwater, aquifer modeling, recharging of dry spring. You can also have the nuclear desalination. The sludge hygienization using gamma rays is also an important aspect in today's time. And also in the harbors, where there is a silt movement, there these radioactive tracers are very, very important. So the gamma ray, you can see, is there everywhere in the industry, in the food processing, in the agriculture, and everywhere. And the fission process through which all these particles are generated, you can see that the electricity from nuclear, it has growing from 1960, except for a small dip that is around the Fukushima accident. There is no looking back for the nuclear energy. Even after the Fukushima, the nuclear energy is still growing. And this is what I'll take, I'll change the picture that after Manhattan Project, what did really happen? And it's a very interesting historical, what it is called, this period is called Cold War and hot physics. You know, this was the period of the Cold War. And there is an important quotation, which I bring it to you. The physicists won the World War II with microwave radar and ended it with atom bomb. So actually, the Second World War was won by that low energy photon, the microwave radar. But the war did not end, and it was ended by the nuclear weapon. And just after the Manhattan Project and the Second World War ended, the focus shifted from the problems of war to the concerns of peace, and that is the peaceful uses of atomic energy, and also, unfortunately, the technological race for the military advantage. And another important thing that happened was that the science moved from the universities to the big laboratories. The entire field of nuclear physics, based on which the fission is explained, it transformed itself into the high energy nuclear physics and then to the particle physics. And the physicists were worrying about the new particles, new symmetries, quarks as the basic constituents of hadrons, GeV accelerators, everything in a big scale. And in this picture, that low energy photon indeed lost its existence altogether. And if you were a young student in 50s or 60s, and if your advisor would tell you that you work on that infrared photon or a visible photon, you would just smirk and say, no, 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 I would work on that high energy photon, the gamma ray. I'll work on the particle physics. And that's the way the whole field of physics changed. But not so long. Then in 1960 entered the lasers. They were armed with the monochromaticity, coherence, extremely low divergence, and very high powers. And this is what, and with these characteristics, that low energy photon now started striking the world of science, technology, and everything that we know of. You can just see the way it happened in 1960. The ruby laser was invented by Maiman, and its first medical application was done in 1962, and it was also used for the chemical analysis. 1964 was a laser rangefinder. 1968 was the refractive eye surgery using lasers. 1969 is a very interesting thing. In the Apollo 11, they carried a big mirror and placed it on the moon's surface. And later on, the scientists on the Earth, they sent a laser beam, and when it reflected back, the beam was detected. Why use laser? Because it's a low divergence. It is to travel such a long distance and come back without spreading it. And by this experiment, the distance between Earth and Moon was measured to the accuracy of 3 centimeters. And then in 1974, you got the supermarket barcode. 1978, you got laser disc players, and so on and so forth. And now there was no looking back for the lasers also. And this is an awesome tool that is, it is in fact taken as a magical solution to any problem that you want to work on. You can work in communication, you do it in entertainment, in medical sciences, in agriculture, anywhere you go, you can use these lasers. So let me not go into the details of this. Give you a little bit flavor how these lasers are being used now. The lasers in industry, very, very strong presence in the laser material processing for the welding, cutting, marking, surface modification, prototyping, micro machining, advanced manufacturing, 3D printing. Also, this material processing techniques entered the nuclear industry. And here are some examples. The coolant channel replacement, which is done in the reactors. Well, it has to be done very remotely, the cutting and welding. And well, the lasers are the right sources for that. Underwater cutting, well, you can do it with lasers. And also the fuel bundles, which are highly radioactive, they're kept in the hot cell. You want to cut them, dismantle them. The only way you can do it efficiently is by using lasers. In 70s, the lasers entered into the nuclear industry in a very, very different way. The nuclear technology, as we know, is based on the fission of uranium-235, which is just about 0.72% in the natural uranium. And some reactors, they need about 3 to 5% enriched uranium. And now this means that 235 needs to be enriched. Its concentration has to be increased. And since isotopes have the same chemical properties, well, you need to find out something else. Then also gave rise to some newer technological advances, which are called the nuclear spin isotope engineering. This is the microelectronics, spintronics, the nuclear spin computers. For example, if you take silicon, it has got 3 isotopes, 28, 29, 30. Whereas the 29 is a very useful isotope. It has got a nuclear spin. And therefore, that is the one which can be used in quantum computers. In the health, well, the nuclear industry gave rise to the radioactive isotopes, which could be gainfully utilized in the diagnostics. But then, if you can have the naturally occurring isotopes whose concentration is extremely low, and you can enrich them by some means, then they themselves can be used as stressors in the body. For example, ytterbium-168, which is used for diagnosis of the heart valves. Typical prices with this whole process is so expensive. The typical price is about $300,000 to $700,000 per gram. And the lasers propose that yes, this can be done. If you have two isotopes, let's say on this picture, I have shown A and B. You can take it as one as uranium-238 and one as 235. Because of the mass difference, their energy levels are not exactly same. They have a very small energy difference, and which is called an isotope shift, which happens to be in megahertz and gigahertz. For ordinary light, these shifts are not visible. However, the lasers can be so finely tuned that you can tune your laser to a particular transition of a B isotope and then apply another laser to ionize it. So B becomes B plus. So now you are creating a mixture of A neutral and B ionized, and just using electric or magnetic fields, you can now separate B plus. And this is what gave rise to the laser isotope separation processes for nuclear as well as non-nuclear applications. And here you can see that you can use an electron gun to vaporize the material. This is a block of material. And then in this vapor, you intersect it with lasers and selectively ionize the isotope that you want. And that isotope, then you can remove by the electric field. It's a very simple way. And I must say that the diffusion process, centrifuge processes, which were developed by the physicists in Manhattan Project. And this is another method which is given by the physicists. And then came the laser fusion, that you can do the fusion using lasers. And the ideas, again, are, I'm going to give you very elementary ideas. The laser beams, if you focus them on a target, then this high power lasers will create a plasma. The plasma will leave that fuel, and during that process, it will result in a compressive force. And that compression will increase the density of this fuel which is kept here. And this fuel can reach the density about 20 times the density of lead, and it starts igniting at that temperature of 10 to the power 6. This is essentially is the process that you take deuterium tritium. It will produce that helium-4, a neutron, and 14 MeV, and it's a huge source of energy, 700 MeV per gram of the fuel. And this is what is happening also in the sun. The sun fuses 500 million tons of hydrogen atoms every second. And that was the energy that we get. We'll come back to this point little later. And then to give you a scale, when Myman developed that ruby laser in 1960, the first laser, it looked like this. And now you look at the lasers which are used for the laser fusion experiments. These are 500 into 10 to the power 12 watts neodymium phosphate glass lasers. This is at the National Ignition Facility of the United States. There are 192 beams. They compress the deuterium tritium pellet to achieve fusion. And the first breakthrough, that is break even, is you supply an energy and the energy you get, it just balances, was achieved sometime in 2013. As the time progressed, the things took a different turn. By 90s, we started achieving ultra-intense, ultra-short light pulses. That is, you could have 1 joule of energy in a pulse of 10 to the power minus 15 seconds. And the peak power of such a light source would be 10 to the power 15 watts. And if you focus it on a target, then you can achieve a focus intensity of 10 to the power 20 watts per centimeter square. Now, we know that the light is made up of the electric field and the magnetic field. For 10 to the power 20 watts per centimeter square, the electric field is gigantic, 10 to the power 12 volts per centimeter or more. The magnetic field is much more than 10 to the power 9 Gauss. And a particle can get an acceleration which is 10 to the power 21 times the small g. And the electrons, which when they see such a light, will produce energetic electrons of more than 100 MeV. And what it has given rise to towards the end of the last century was the acceleration of particles, electrons and protons, production of gamma ray from these low energy photons, initiating nuclear reactions with these low energy photons, and the neutron production. You can have now the neutrons and demand, and also the isotope production, the isotopes which were not possible to generate through the fission process in the reactor. Now you can start doing them from. How did it happen? A bit of physics I should give you, otherwise it will be just a magic. You have a laser pulse which you put on a target, then the target will evaporate. There's a huge energy there. It will form a plasma. In the plasma, you will have the electrons. And these electrons, they will see the laser field, electric field, and they will get accelerated. And they will attain very high energies. Now, these high energy electrons, you can start with the high Z material like tantalum. Now, this is a process where what is it called as a bronstalum, that the high energy charged particle, when it is deaccelerated, it will generate a photon, and the maximum energy of that photon is the energy of that charged particle. So if I have got a charged particle of 10 MeV, which I have generated in this process by laser acceleration, then I can generate a photon of 10 MeV. So I'm generating a gamma ray. And once that gamma ray, it falls on any nuclei, then the nucleus get into the, what is called as the technical term is the giant dipole resonance, where the protons and neutrons starts oscillating in opposite ways. And this giant dipole resonance gets settled, stabilized by emission of a neutron. So now what you have here is a photon of energy 1 electron volt. It produces electrons of MeV energies, which in turn produce a photon of MeV energies. And those MeV photons further interact with the nucleus and give rise to the neutrons and do the nuclear transmutation. And you can see here, these are all the experiments which have been done. Take gold, and it gold 197 turns into gold 196. You can also do the fission process using these lasers. That is the uranium-238, which does not undergo fission, but it has a fission threshold of 5 MeV. So you can generate this 5 MeV gamma and start doing that. Or you keep that uranium with this sort of a targets, and the neutron emitted through this can do the neutron fission reaction. Now, this is a wonderful application that people are looking for. The nuclear reactions, the nuclear reactors, they generate a lot of nuclear waste, and only some of the isotopes are really troublesome, like 137 cesium and 129 iodine. If you can take care of them, then your whole nuclear waste can be called almost like a benign waste. They got a half-life of 30 years for 137 cesium, whereas 15 into 10 to the power 6 years for iodine 129. The idea here, what the laser physicists have proposed, is that if I can take an ultra-intense laser and produce the gamma ray, as I shown you in the previous slide, that gamma ray can interact with the cesium-137, and then it will set into the giant dipole resonance, and it will get stabilized by emission of a neutron, and this cesium-137 becomes cesium-136. And cesium-136 has a half-life of 12.6 days, and it emits a beta and becomes 136 barium. It's a very stable isotope. The same thing you can see here, 129 iodine gives rise to a neutron and produces 128 iodine, another beta emission, and gives rise to 128 xenon stable. Now, in the laboratory scale, all these experiments have been successful. And what is required is to look at in the large scale. And if this succeed in a large scale, then this could probably give rise to a solution to the nuclear waste problem that we're talking about. As I said, this whole process generates neutrons, and therefore now there are portable neutron sources. and where you can get neutrons on demand. You shine the laser and you start getting the neutrons, and you switch off the laser, then the neutrons source gets extinguished. And these sources now are becoming popular. And one of the reasons for this is you can see you can get neutrons to the something like 10 to the power 8 neutrons per joule of the laser. And the important thing here is the cost. If you use an accelerator, the proton beam doing the spallation, the costs are exorbitant, 1 billion or so, whereas all this could be done at a fraction of that cost. And therefore, these laser-driven neutron sources have become popular. And now the lasers are entering indirectly with the acceleration of the particles. And that you can see from this view graph, that the accelerator beam energy is progressed 10 times every 6 years over last 70 years. So the whole history is that of 70 years, whereas the peak power lasers has increased 10 times every 3 years. And there is a fundamental limit which comes for accelerating particle in the conventional accelerators, because there is a electric breakdown that takes place, whereas no such problem is anticipated. And therefore, beyond LHC, now the accelerators are going to be the laser-driven accelerator. And now you can see this whole picture, how it has evolved over the last 20 years, is that earlier we used to talk about a proton accelerator with a huge ring of several kilometers. Now all this can be done by tabletop lasers. Earlier lasers also used to be huge 3-4 storied buildings, but now everything you can accommodate on a table. Of course, it's not a table that where you write, it's a table of 3 meter by 3 meter. You can accommodate the entire laser system, which can do all these laser-driven systems like proton acceleration, electron acceleration, neutron generation, or even transportation. And finally, I should also connect you to the solar energy, where the low energy photon has struck again. And now this is, while all these developments were taking place in the nuclear physics, high energy physics, and also in the lasers, well, there were people who were looking at that dream of making solar energy a viable one. That is to revisit about 5%. And now, today, we are talking about the silicon photovoltaics with a minimum efficiency of 15%, and it can go up to 22%. So we have gained a factor of 4 in the efficiency. At the same time, the prices of the silicon photovoltaic cells have dropped considerably. And this is, you can see that in 1977, the cost of producing solar energy per watt was $1.76, whereas by 2015, it reduced to $0.3 per watt. And what is it? I mean, there is just like in computers, we talk about the Moore's law. Same thing in the solar energy, there is a Swanson's law, that when the global manufacturing capacity for solar panel doubles, the average price of these panels drop by 20%. And realistically, if you put all these figures, that in 10 years, the prices would drop by 75%. And that's the phenomenal change that has taken place. And that change has taken place in last 10 years. And I'm bringing to you the latest one, the solar cost from 2010, they have dropped about 5 times. And you can see the figure, which is here in the orange for the India. And it is now coming out to be less than even $0.05 per watt. So that's the kind of gain that one is now having with the solar energy. And therefore, we now, if you compare the nuclear power versus solar power, as we said, that the solar power started growing only after the slash in the prices of the solar photovoltaic. This is the solar power as it is, starts somewhere around 2010, and then it is growing. Current worldwide capacity is around 700 terawatt hour. But this is a small fraction of what is going on in nuclear. But this picture is for the whole world. And this may give you a different ideas that solar is not really working well. Well, you can see individually, and you can see what is happening in US and Europe. They already have the nuclear power stations. Their energy needs are somewhat satisfied, and they have taken to solar. So there is no problem about the nuclear energy. They have plenty of it. The other energy sources are plenty, but they're also trying to change over to solar. In Europe, you can see the nuclear energy has decreased. This is particularly because the Germans have dropped their nuclear energy program and they want to go ahead with the solar energy. But the major change you can see is in those energy hungry countries like India and China. They still need large powers to generate. And this is what is happening to China. Now, the rate of growth of solar energy is much faster than what is happening with the nuclear energy. And in India, this is the picture that in last few years, there is a phenomenal growth in the solar energy in this country. And that brings us to a small question that do we choose nuclear energy or solar energy? Well, you should never have that question in your mind because the selection of energy depends on what kind of energy mix that you're going to do. And but just to give you a feel, and I must say that many a times we refer to the figures which are quoted by the Americans or the Western scientists. We need to create these numbers for ourselves, except for the first figure, which is the nuclear energy is a concentrated energy source. 1 gram of 235 fission produces in a day produces about 1 megawatt, whereas solar energy is a dilute and intermittent source, and the average solar irradiance in India is about 5.97 kilowatt hour per meter square per day. So this is, and certainly it would mean that in order to tap this energy, you would require large land area. But that is not so, because if you take a nuclear power station and also add the area of the uranium mines in it, then you can see the land use is about 2.1 kilometers square per terawatt hour for nuclear, and in this case it's about 3 times higher. Nuclear energy is expensive. It's about 10 factor of 10 you can place, and it has got a large gestation period. Whereas solar power station you can set up in a very short period of time. They are cheaper also and rapid installation. Well, the nuclear energy produces nuclear waste, but one has to take this particular line with a pinch of salt. That the radioactive waste is also a useful resource if you can take care of those radioactive isotopes and use them in industry, medicine, or agriculture. In solar energy, the waste is supposed to be benign, but we are still in the initial phases of the solar energy development. After 20 years, suppose the solar panels have to be discarded, there will be tons of silicon waste, and what we're going to do, we still do not know. This one issue is goes in favor of solar energy. Once you set up nuclear power station, the land use is permanent because you cannot use it for any other purpose. So suppose after 50 years, somebody says, oh, the energy technologies have changed. Can I replace your nuclear power station with another? Well, it's going to be difficult. A lot of decontamination will have to be done. But the solar energy, well, it's very easy to reappropriate the land. Just remove the panels and there you are. But this is not the way one decides what is the energy choice. Energy choice is decided by what is safest and what is the cleanest energy source. Safest means does it cause any deaths due to the accidents? And the cleanest is what is the greenhouse gas that is emitted. Again, this data is for all over the world. You can see here the various energy sources, coal 25%, it contributes 25% to the world energy pool, oil 31%, natural gas 23%, biomass is still contributing 7%, hydro is 6%, the nuclear is 4%, wind is 2%, and solar is just 1%. And that is what is the picture. But you can see the deaths. Deaths due to the coal mining, and also the pollution deaths per terawatt hour is 25, oil is about 18, natural gas is about 2.8, biomass 4.6. And look at all this. They're in 0.02, 0.07. This 0.07 also includes the figures from Fukushima. Wind is 0.04 and solar is 0.02. Whereas the greenhouse gases, you can see huge greenhouse gases emitted by the first three. The biomass depends on the quality of biomass, which is about 78 to 230 tons per gigawatt hour. Hydro is 34, and the nuclear, wind, and solar is in single digits. And therefore, if you want to choose now the energy mix, this is where you concentrate. That these are the safest and the cleanest energy sources, and the world should be looking forward to this. Now, what I have done in past 40 minutes is to give you a tale of two photons. One was a low energy photon and one was a high energy photon. The low energy photon was the most popular one before 1930. People were wondering about it. They used it for all their things. And then suddenly that large energy photon comes and this small energy photon goes into the background. But then you also remember, this is the message for the younger students here. They should not be worried about such things. You should strike back. You should work hard and make yourself indispensable. And that is what that small energy photon did. By taking the form of a laser or by the solar energy, it has again put itself into the competition, and in a very, very positive way. This tale of two photons might remind you of Charles Dickens' famous novel, A Tale of Two Cities. But I must tell you, what I have told you is not tale of two cities. It's a tale of a same city, but two different parts of the same city. The same electromagnetic spectrum, and the low energy photon and high energy photon are part of it. So there is no way, there is no logic to distinguish except in terms of its energy, and that is all. At the same time, we also must remember all that low energy photon, the sun as the source. The sun derives its energy from the nuclear processes. At the core of the sun, there is a fusion process is going on, which generates heat. The radiation is also generated there. But then there is a big convective zone which protects us from that radiation coming from the core. And what really comes out on the surface is only the heat. And that heat at the surface corresponds to a temperature like 5,000, 6,000 K. And that is what the sun generates, that black body spectrum corresponding to the 600 K, which is that low energy photon spectrum that you see, and that is all. So even that low energy photon has the same origin as the high energy photon. And therefore, you can always say this, that solar is also nuclear. There is no difference. If you look at from the origin point of view, then they are all generated. The basic process is a nuclear process. With this, I thank you for your patience, and thank you very much.
Bhagwat sir.
Thank you. Thank you, sir. एक मिनट है जरा, थोड़ा टाइम दो. भागवत सर अनम्यूट कर. हाँ भागवत सर, थैंक यू वेरी मच सर.
Yes, sir.
थोड़ा उठा Thank you very much, Jagtap sir. Such a wonderful, nice, informative lecture.
Yeah, thanks.
We are very much thankful for eagerly listening about the radioactivity, the uses and the applications and the solar energy in this current scenario. Thank you very much on behalf of NMSA and the Rayat Shikshan Sanstha's Karmaveer Bhaurao Patil College Vashi. Thank you very much, sir.
You're welcome.
Next speaker is Dr. Madhav Mala.
हॅलो सर, रिझल्ट घ्यायचा अगोदर.
हा, result घ्यायचा.
रिझल्ट
May I now request Secretary of this today's World Nuclear Energy Day, Dr. Bhaurao sir, to announce the result. So on the occasion of this World Nuclear Energy Day, we conducted 3 competitions and we selected 3 winners from the state level competitions in the presence of Honorable Chief Guest Dr. Jagtap sir. Bhaurao sir is going to announce the names of the winners of the various competitions that is organized by Department of Chemistry and the NMSA. Over to Bhaurao sir.
ओके सर. ऑन द ऑकेजन ऑफ दिस सर स्क्रीन शेअर करू. ही बंद कर लागेल ना. नाही
बंद करतो मी.
चल एक मिनिट.
कंटिन्यू.
येस सर. ओके. ऑन द ऑकेजन गुड
Share your screen.
स्क्रीन कितने सर?
Please share your screen.
Yes, sir. Screen
yes.
केली. On the
It's
occasion
visible.
of World Nuclear Day, under the guidance of Honorable Principal Dr. Shubhra Nayak Madam, my HOD Dr. Y. Gaikwad sir, and other colleagues of the department, we have conducted the quiz. MCQ test was carried on 28/11/2020 in collaboration with Navi Mumbai Science Association. For FY-BSc, 313 students participated along the state. For SY-BSc, 340 students are participated. For TY-BSc, 292 students are participated. So this is the huge response getting us from all over the Maharashtra and from different universities. FY, SY and TY for the chemistry purpose. We have also carried out one general science test for FY, SY, TY, BSc. For FY, BSc, we get 380 participants. For SY, BSc, we got 319 participants. And for TY, BSc, we have 412 participants. Beside that, we have carried out the essay competition on the basis of certain criteria of energy. This essay competition is based on nuclear energies and their concepts. For FY-BSc, 145 students are participating all over the state, Maharashtra. Then for SY-BSc, 164, and for TY-BSc, 187. One of the feature of this competition is that some students are participating from Madhya Pradesh, some are participated from the Chhattisgarh, and even though for the general science quiz, we have got 3 and 4 participants from Saudi Arabia. So this is one of the success of our competition. Overwhelming response of this competition, we have carried out this competition on the basis of Google form. So I will announce the result for the FY-BSc General Science MCQ. The 6th rank goes to the Yadnesh Anil Yadav from Karmaveer Bhaurao Patil College, Vashi. Then 5th rank goes to the Triveni Sunil Bane from YC Institute of Sciences, Satara. 4th rank goes to the Utkarsha Patil from Vidyavartini's SES College, Palghar. Third rank goes to the Dahiwadi College, Dahiwadi, Khetre Vishal Sanjay. Second rank goes to the Abhishek Pawar, YCIC Satara, Yashwantrao Chavan Institute of Sciences, Satara. And first rank goes to the Sresh Nilimani, that is Anna Sahib Vartak College. So this is the result for FYBSc student. There is a huge competition between them. Then for SYBSc General Science result, I will announce. Sixth rank goes to the Vijay Lakshmi Rumanna Pathan from Vijay Singh Yadav College, Pet, Wadgaon. Fifth rank goes to the Deepak Babaso Kuranwade from RCSC Kolhapur. Fourth rank goes to the Utkarsha Ravindra Sonavne. She is from Karmaveer Bhaurao Patil College, Vashi, Navi Mumbai. Third rank goes to the Mohini Sanjay Khalane, Zulal Bajirao Patil College, Dhule. Second rank goes to the Sonal Saurabh Sorge. She is again from KBP College, Vashi, Navi Mumbai. And first rank goes to the Yash Nayan Tokle from DG Roparel College, Mumbai. Then for TYBSc, sixth rank goes to the Vikas Balu Tambe, New Art Science College, Parner. Fifth rank goes to the Wakchore Rupesh Madhukar. He is from NACS, New Arts Science Commerce College, Parner. Fourth rank goes to the Karmaveer Bhaurao Patil College, Vashi, Rutika Satyavan Kaure. Third rank goes to the Pratibha Devghare from Karmaveer Bhaurao Patil College, Vashi. And second rank for the chemistry MCQ goes to the Nahira Nazir Menon, SIS College, Sion, West. And first rank of the TYBSc General MCQ goes towards our TYBSc student Nazin Nasir Khan. She has got 86 marks. This is the highest marks that I have got all over the competitions. So I congratulate behalf of the Department of Chemistry. For Chemistry General Quiz, for FYBSc, first rank goes to the Deepak Babasaheb Purnwade, RCSC, Kolhapur. Fourth rank goes to the Prabhnya Sanjay Salunke, Modern College, Vashi, that is Karmaveer Bhaurao Patil College, Vashi. Third rank goes to the Utkarsha Patil, Vidyavardhini ASA College of Science, Vasai Road, Palghar. Second rank goes to the Patil Prathamesh Santosh, KBP College, Vashi, Navi Mumbai. And first rank goes to the Kulkarni Anuksha Suhas. She is from MJ College, Jalgaon. Then for SYBSc, there is again huge competition. Fifth rank goes to the Narahari Tule from Karmaveer Bhaurao Patil College, Pandharpur. This is our Sanstha's college, which is located at Pandharpur. Fourth rank goes to the Neha Devkant Tiwari from Vidyavartini Anna Sahib Vartak College, Vasai. Third rank goes to the Pranay Janardhan Indulkar, Ruparel College, Mumbai. Second rank goes to the Om Kailas Suravse, KBP College, Pandharpur. First rank goes to the again Yash Nayan Tokle. This student got first prize in General Science also. He is from Ruparel College. For TYPSC chemistry students, sixth rank goes to the YCIC Satara. Fifth rank goes to the Fija Dastagir, Karmaveer Bhaurao Patil College, Pandharpur. Fourth rank goes to the Dhanavde Vaishnavi Mahesh, SSGM College, Kopargaon. Third rank goes to the Shivani Misra, our TYBSc student, Karmaveer Bhaurao Patil College, Vashi. Second rank goes to the Shubham Sandeep Sawant, Anna Sahib Vartak College, Vasai. And first rank goes to the Nazir Menon, SIS College, Sion, West. So last part of this is the result of essay competition. In essay competition, most of the students written essay very beautifully. So it is very difficult. It will take around 10 hours to identify the winners. So seventh rank goes to the Kalwanti Kavandar from Vivekananda Education Society, Chembur. Sixth rank goes to the Devika Mohan C. Chauhan College, Ujwala Sharma from Devika Mohan C. Chauhan College, Dadra Nagar Haveli. Fifth rank goes to the Neha Sandeep Singh from Veer Vajekar College, Punde. Fourth rank goes to the Rajasvi Raju Gharge. She is the student of Karmaveer Bhaurao Patil College, Vashi. Third rank goes to the Tanusri Mahesh Shevde from Karmaveer Bhaurao Patil College, Vashi. Second rank goes to the Patil Viren Vivekanand. He is a student of SGM College, Karad. This is our Sanstha's college. And first rank of essay competition in SYBSC class goes to the Tanuja Balasaheb Pawar. She is from Karmaveer Bhaurao Patil College, Vashi, Navi Mumbai. Then for SYBSC, sixth rank goes to the Ritika Goethale from Karmaveer Bhaurao Patil College, Vashi, Navi Mumbai. Fifth rank goes to the Muskan Alman Patel, RBNB College, Sirampur. Fourth rank goes to the Priyanka Satish Sutar, YCWM Varnanagar, Kolhapur. Third rank goes to the Sejal Dinesh Yadav, RK Talreja College, Ulhasnagar. Second rank goes to the Wasifa Haidutullah Patel, RC College, Kolhapur. And first rank goes to the Achal B. Upadhyay, Karmaveer Bhaurao Patil College, Vashi, Navi Mumbai. She has one of the remark in FYBSC, she has also got the first rank. For TYBSC, first rank goes to the Sonali Ramchandra Kalbag from CKT College, Panvel. Fifth rank goes to the Turkane Prajakta Sandeep, SSGM College, Kopargaon. Fourth rank goes to the Rajeshri Ashok Barkade, Dahiwadi College, Dahiwadi. Third rank goes to the Pawar Sankalp Ajay. He is our TYBSC student, Karmaveer Bhaurao Patil College, Vashi, Navi Mumbai. Second rank goes to the Sonali Suresh Bade. She is student of KBP College, Vashi. And first rank goes to the Rushali Dhananjay Pawar, Yashwantrao Chavan College, Islampur. So, under the guidance of our HOD, Mr. Y. Gaikwad sir, principal, Mrs. Dr. Shubha Nayak madam, and all these colleagues and Navi Mumbai Science Association help us to carry out this huge competition. We have converted this competition college level to the state level. So I thankful to all my colleagues, my friends, and without which competition is not successful. All participants, I congratulate all participants on behalf of Department of Chemistry, and I stop here and I forward to the Dr. A.M. Bhagwat sir to introduce next speaker. Thank you, one and all. Thank you.
Thank you, Dr. Wadhwa sir. I'm sorry that I lost the link just after the talk of Dr. Jagtap was there. So with permission of everybody, let me thank him, belated thanks to him for his nice presentation. I would say he was dealing with photons and they were scintillating photons. And their scintillations have a very long life in this particular case. And we will remember you for quite some time. And maybe, if you don't mind, we will again disturb you in future and invite you and have interactions on what is going on, physics, chemistry, or science as such. And would like the students to be entertained by ideas like this, that what is a Fermi estimate? And while telling them, they should also get a feel of science. And if they get the feel of science, I think we will have done our duty to the nation. With this, I stop, and now I introduce. Yeah. But Dr. Madhav Malia completed his MSc in Applied Chemistry from Cochin University of Science and Technology in the year 1999. After a brief stint in National Chemical Laboratory, Pune, he joined BRC Training School in the year 2001. In 2002, after successful completion of training school program, he joined Radiopharmaceuticals Division, BRC. His main area of research is development of technetium-99m tracers with small biomolecules, antibodies, and peptides as targeting vectors for diagnosis, and a possible extension of this idea to corresponding uranium isotopes of 186 and 188 numbers. Analogs, these are the analogs, and again their uses for therapy. He completed his PhD in chemical sciences in the year 2013 after successfully defending his thesis titled Synthesis and Evaluation of Technetium-99 labeled tricarbonyl complexes of differently substituted nitroimidazole as agents for targeting tumor hypoxia. He has over 50 research articles in various peer-reviewed journals. He is the recipient of following awards. 1. Homi Bhabha Gold Medal for securing first rank in BRC Training School in Chemistry discipline in the year 2001-2002 batch. Second, prestigious DAE Scientific and Technical Excellence Award uh, for the year 2015. And third, Dr. Tarun Datta Memorial Young Scientist Award from Indian Association of Nuclear Chemists and Allied Scientists for the year 2019. Presently, he is also a faculty member at Homi Bhabha National Institute, Mumbai, as Associate Professor in Chemistry. While mentioning the third award of Dr. Tarun Datta Memorial Young Scientist Award, what I want to underline is Young Scientist Award. So here we are going to have a presentation by the young scientists, and I am sure that in the near future he will have his list of awards will be growing at a rapid rate. So today he is going to share with us his thoughts on the topic radiation for cancer detection and cure. Dr. Malia, please. Gaikwad sir? Gaikwad sir? Gaikwad sir?
Yeah, bola bola. He is very visible now. Sir, you proceed.
I think, I hope you can hear me.
Yes, sir.
Fine. In fact, I am having trouble with so I'll be actually presenting bye. So let me see. Okay, I think I'm back.
Madhav Malia, you have to close one of the mics. One of the mics you shut down. Okay. Yeah, that's right. That's okay. Now it will go. Now it will be all right.
Fine. So as I was telling, I have trouble with internet. So I hope for next 30 minutes, internet will cooperate with me. And before I start, let me thank the organizers for giving an opportunity to talk to you. And now let me go to my presentation now.
No, it's feedback.
Yeah.
Okay. Now it is okay.
Now it is fine?
Fine. Fine, sir.
Yeah. Can you see my presentation? Can you see my presentation?
No, sir. It is not visible, sir.
Hello. Can you see my presentation? Not visible. Okay. So it is presenting for everyone, but I don't know why you are not able to see. Can you see it now, please?
No, sir.
Not
Please
yet.
share again. Now it is visible, sir.
Yeah, fine.
Just select the screen.
Now it's coming.
Not fully.
Is it visible now?
No, sir. No, sir. It is not visible.
Not yet. Okay. But now it is showing. It is processing for everybody.
Sir, not looking the screen. Yeah.
Are you seeing the screen now?
Now only we see yours presenting the screen to everyone. But the content that is not visible.
The same here also. Okay. So, Rajarajan sir, any suggestions, please?
Can you use the Google Chrome, please?
Yeah,
Chrome
I'm
browser.
using Google Chrome only.
That looking Firefox, that browser.
Acha, okay. Let me check. Should I select present your entire screen or present window?
Present window only, sir.
Okay, fine. Can you see now?
Yes, it is visible now. Yes, sir. Yes, sir, visible.
Is it visible? Okay, fine.
Yes, you continue, sir.
All right. So thank you so much, and so sorry for this technical glitches.
You can make it full
So
screen.
just now the previous speaker we heard. Yeah, it is full screen only.
Click on the last the PowerPoint presentation menu. Just click F5. Hello, sir.
No, still I am having. Can you see the screen now?
A screen is visible. Just use the PowerPoint presentation, that F5 full screen.
Yeah, I am doing. I can see full area.
At the end, the bottom, there is the 70% दिखता है. So you can click that button nearby 70% last. Then you can see full screen size. Slide.
Okay. I'm extremely sorry. I'm not able to do that.
Hey, your screen is visible now, sir.
Now can you see it, please?
It is visible, but just you click the F5 in a plus PowerPoint presentation mode. Don't zoom it, sir.
Okay.
So see the 116 at the end. दिखता है ना आपको 116? So close to that, you can click that icon.
Yeah.
Then it becomes a full screen, a slide.
Now it has become full screen for me. What about you?
It will be visible to all. Same like that.
Okay. So is it okay now? Can I continue?
Yes, you continue, sir. Please.
Yeah, fine. So much and sorry for the technical glitches. So today the my presentation is radiation for cancer detection and cure. And you already got a session regarding this, the previous speaker, Dr. Jagtap. So if you look at the basic definition of radiation, it says it's an emission or transmission of energy in the form of waves or particles through space or material medium. And the second thing that probably comes to your mind is the electromagnetic spectrum itself, which is nothing but arrangement of these waves in the increasing order of frequency or energy. And basically, most of you must have also known it can be assigned to different regions, like we say radio waves, microwaves, infrared radiation, visible light, X-rays, gamma rays, and alpha and beta radiations, which are basically from nuclear origin. And we associate these waves to different applications also. Like, for example, radio waves we assign to radio, microwave ovens, where a household as a microwave oven. Then we have infrared radiation, which basically use it in remotes, and then X-rays, gamma rays. And I can also associate these different rays to healthcare applications, just like for day-to-day applications, for healthcare applications also. What I mean was, for example, radio waves, I can assign it to magnetic resonance imaging, which you must have heard of. X-rays, you can assign it for X-ray imaging. And gamma rays, you can assign it for SPECT and PET imaging. This is very common nowadays. You must have heard about this name, SPECT, PET. And alpha and beta radiation, you can assign to cancer therapy. This, I'm not sure whether you know it or not. But today we are going to be concentrating on this particular application. So the moment we hear about the words like radioisotope and radioactivity, the picture that comes to our mind is this. And we want to keep away from it. That's quite natural. But now you must have already got an idea that these radioisotopes have immense applications in industry, agriculture and food technology, and also in healthcare. And today we will be concentrating on healthcare applications of radioisotopes. Now, if you look at the radioisotopes in healthcare, we can broadly divide them into three categories. One is brachytherapy, teletherapy, and use of radiopharmaceuticals. Now, within this short time, it will be very difficult to cover the entire spectrum of applications, but for the time being, we will be concentrating only on radiopharmaceuticals which can be used for both diagnosis as well as therapy. Now, even if we confined ourselves to radiopharmaceuticals in healthcare, we will see that it has immense applications in different fields like cardiology, nephrology, and neurology. But today, again, we will confine ourselves to oncological applications of radiopharmaceuticals. So now what is oncology? You must be knowing it. It's a branch of medicine that deals with prevention, diagnosis, and treatment of cancer. We will not be concentrating on the prevention part, but rather we will confine ourselves to diagnosis and treatment of cancer. Now, in India, there are many cancers prevalent, and some of the important cancers very much prevalent in India are liver cancer, stomach, lung cancer, breast cancer, thyroid cancer, and prostate cancer, and many more, of course. So, what is a cancer? So, basic definition of cancer says it is a disease in which abnormal cells live without control and can invade other parts of the body. Now, if it divides without control and get confined to a particular part of the body, then it would have been easy to manage because we can just basically remove that part. The very problem with cancer is that it has that ability to invade other parts of the body. What happens is that from the primary tumor sites, some of these cancer cells can dislodge from that primary tumor site, and they can enter into the bloodstream and travel through the bloodstream to other parts of the body, and they can start growing at that new location, and that creates a lot of problem. And we say the cancer has undergone metastasis, means it has spread to other parts of the body. So, how to detect cancer in the body? So that is our basic question. How do we do that? So let us assume that we are presented with a patient with cancer metastasis. That is, this cancer has spread throughout the body. So what is our challenge here? The challenge here is that cancer is inside of the body most of the time, and hence it is very difficult to see from outside. And also, it may be in one or many places. It can be small size or it can be a large. So these are our challenges. How can we see something which we cannot directly see? So what is a possible solution? A possible solution could be that if we have a safe to inject substance which can accumulate preferentially in cancer and send a signal that can be detected from outside the body, then we can have a solution to this problem. And it is here that radioisotope comes very handy as a source of signal which can be from a fake object. Now, I assume that you already have some background information about radioisotope and radioactivity. So I'll not spend too much time on this. We'll just brush these subjects. So radioactivity is a phenomenon of spontaneous emission of radiation by an unstable nuclei. And you also must be knowing that this great scientist Henry Becquerel, the person who discovered it, and this unstable nucleus is like an angry man who starts yelling at us because he is angry. And then during this process, it releases excess energy in the form of a radiation. So the radiation that basically we get from an unstable nuclei is gamma radiation, alpha or beta radiation. And once this excess energy is released, then the nucleus becomes stable, just like this angry man cools down. And I also assume that you are familiar with the sources of radioisotopes, which are basically nuclear reactors and cyclotrons. Again, I will not be dealing too much with this radioisotope production part. That can be a subject matter of another some other point of time. This I've seen many a times. It essentially shows the penetration power of different radiation emitted by an unstable nuclei, that is radioisotope, alpha, beta, and gamma radiations. Now, if you look at the penetration wise, gamma rays are very much penetrating. They can even penetrate very thick concrete blocks, followed by beta. Here, I just want to remind you that beta radiations are two types, one is beta minus and the other is beta plus. That followed by alpha radiation. Now, if I pause you one question, so which radiation can act as a signal from inside the body? Naturally, the answer should be gamma radiation because these are the radiation which can only penetrate. Alpha and beta radiations cannot penetrate our body tissue. Therefore, high penetrating gamma radiations can be used for diagnosis. Now, what about positron, that is beta plus? Beta plus is very interesting in the sense beta plus, once from the nucleus of an unstable isotope, it can combine with an electron from the surrounding, and in the process, both of them vanish and produce 511 K gamma radiation, which moves diametrically in opposite direction. And this entire process is called annihilation. So essentially, what I mean to say is that even though beta plus per se cannot give a signal, beta plus upon annihilation with an electron can produce 2 gamma radiation, which can be used for diagnostic purposes. So we'll slightly modify our statement. We will say radioisotope emitting gamma rays and positrons can be used for diagnosis, and they are called diagnostic radioisotopes. In a similar way, alpha and beta radiations are used for therapeutic purposes, and the therapeutic radioisotopes. Fine. But how can we send the radioisotopes? We found that gamma radiations are very good for penetration and you can detect it from outside the body. But unless these radioisotopes are sent to our target tissue, which is the cancerous tissue, how can we do that? So now we are going to address that problem. Now it is like, you want to go to a certain destination and you know how to go there. Then will you ask anybody? No. You know how to go there, so you will simply go. But there can be another situation where you want to go to a certain destination, but I don't know the way. So what is an option for me? What I will do easiest way is either take an auto or bus, because most of these people, they know to take bus there. So that is basically what we do in this radioisotope applications as well. And you understand what I mean by this in subsequent slides. So let us take the case of iodine. Iodine is one radioisotope with its way. It knows its ways to thyroid. Now, thyroid is a small gland present somewhere around our neck. And thyroid has the inherent ability to absorb iodine from our diet. That is very interesting. Now, what does it absorb? Thyroid utilize iodine from our diet to biosynthesize 2 important hormones, that's T4 and T3. What it means essentially is that if we can monitor the iodine uptake, then it actually provides us with the functional status of thyroid, whether the thyroid is early or not. But the non-radioactive that we take in our diet every day, it is non-radioactive. So we cannot track it because it doesn't give out any signals. But fortunately, there are many radioisotopes of iodine which we can choose from. For example, 123 iodine, 124 iodine, 123 iodine emits gamma radiation, 124 iodine emits a positron. Both can be used for diagnosis, but they are produced from cyclotron. Now, cyclotrons are coming up in India a large way, that is true, but still, such isotopes are difficult to get and a bit costly. But there are some other interesting isotopes like 125 iodine and 131 iodine, which can be produced in a nuclear reactor. But 125 iodine, as you see here, it emits low energy gamma radiation. Now, low energy gamma radiation, they cannot really come out of the body in good amount, resulting in poor detections in the body. So therefore, most of the people don't use 125 iodine as a choice. But 131 iodine is having a gamma radiation as well as a beta radiation. Important. Just note that it has both gamma as well as beta radiation. That gamma radiation we can use for imaging purposes. Now, why we are able to do this? We are able to do this because radioisotope of iodine behave exactly the same as non-radioactive iodine. That is why we are able to use 131 iodine for tracer application, because chemically 127 iodine, 131 iodine, they are the same. And we are going to use it as iodide minus. Fine. So to evaluate functional status of thyroid, what we are going to do, we'll ask the patient to take sodium 131 iodide solution, that is sodium iodide solution in which iodine is 131. I will give it in very small doses because our idea is not to give access to those to the radiation dose to the patient, but use the gamma radiation for our diagnostic purposes. After taking sodium iodide solution, we'll wait for some time, and then we'll ask him to lie under a called gamma camera, and we'll start monitoring his thyroid region. And then the gamma camera detect the radiation coming out of thyroid and construct it into an image. Here I have shown you a two-dimensional image that you are getting. That intense spot that you are seeing is the radiation coming out of thyroid. As I mentioned to you already, thyroid has two glands, so you can two oval shape. You can see each gland of thyroid. Now just look at the first picture of thyroid. You can see that the intensity is almost uniform distributed in both glands. So that is how a normal thyroid looks like. But by looking at the other two images, you are pretty much sure that thyroid is abnormal. Now, both of us are experts, so we cannot relate properly, but for a learned nuclear medicine physician, he can not only say that this thyroid is abnormal, but he can even say whether it is hyperthyroid or it is hypothyroid. And that much information he can get from these scans. And mind you, all these things are done non-invasively. We are not doing any surgical procedure on this patient. And that is the specialty of Mumbai. So just now what I presented is an example of use of radioisotope for organ function evaluation. Now let us consider the other case. I don't know the way. The radioisotope says, okay, I'll be helpful to you, but then I don't know how to do an organ or certain cancer tissue. Fine. So what we do, we'll use a suitable vehicle. And that is how the concept of radiopharmaceutical has come. So here what we do, we take a suitable radioisotope, so that is a passenger, you tag to a biomolecule. Now the biomolecule will design it in such a way that these molecules, when inside the body, can go to a certain target tissue. It can be cancer, it can be an organ, it can be anything. So that is like our bus. And once we combine this radioisotope with a biomolecule, what we get is a radio molecule. And just like we have different buses for different destination, we can have different radiopharmaceuticals for different types of cancers. Fine. Now these radiopharmaceuticals are two types. One is diagnostic radiopharmaceutical and the other is therapeutic radiopharmaceutical. The name itself implies what it is meant for, but just for the sake of clarity, if we attach a diagnostic radioisotope to a biomolecule, what we get is a diagnostic radiopharmaceutical. And some examples for very commonly used diagnostic radioisotopes are fluorine-18, technetium, iodine-131, gallium-68, etc. Now, instead of diagnostic radioisotope, if you are attaching a therapeutic radioisotope to a biomolecule, then what you get is a therapeutic radiopharmaceutical. And some of the common examples for therapeutic radioisotopes are lutetium-177, iodine-131, and tritium-90. So how do we do cancer diagnosis using radiopharmaceutical? So I'll just take an example and then try to explain to you the many different ways we try to address this problem. So the example that I'm going to take is 18 fluorine labeled fluorodeoxyglucose, FDG in short form, which is also the molecule of millennium. So as the glucose, the term, the word glucose, it's an analog of glucose, which can be used for diagnostic imaging. And here we are trying to mimic those. How to do that? So as I already mentioned, our body is made up of different type of cells, and these cells, when undergo mutation, they start growing abnormally, resulting in the formation of a cancer. Now, once this cancer grows, the cells start dividing very rapidly, and all these cells require energy for their cellular function. Now, from where does the energy come from? The energy comes from metabolism of glucose, right? So if you look at this GIF image, what I want to show you here is that the normal cells as well as fast dividing cancer cells require glucose for their survival. But the rate of uptake of glucose for cancer cells will be much, much more than that's the point that I want to bring out. So fast multiplying cells need more glucose. This is easy to understand. Why is it so? So here our bus is glucose. Now through some radios, I can modify this glucose and insert 18 fluorine. And we get 18 fluorine FDG, fluorodeoxyglucose. We call it deoxyglucose because if you see here, what we are essentially replacing one OH group, that is hydroxyl group, with 18 fluorine. So when you replace the OH group, you are removing one oxygen, and that is why we call it fluorodeoxyglucose. One oxygen is less. And what you do? We are prepared fluorine. It goes through several cycles of quality control checks because we are finally going to administer into human. This is mandatory, and all regulators are there. We will listen to subsequent speakers after. So once we inject this 18 fluorine FDG into human patient, what is going to happen? FDG will spread throughout the body, will reach normal cells as well as cancer cells. But as I already mentioned to you, 18 fluorine FDG and glucose behave the same way. So the cancer cells, which has a tendency to use more glucose, they'll also take up more of 18 fluorine FDG. Normal cells will also take up 18 fluorine FDG to a lesser extent. This important point is, it is very important to understand this point. Now what we do, and ask the patient to lie under a device called gamma camera. The camera will scan the patient from head to toe, recording the radioactivity coming out of the body. Then we'll manipulate that information and present it to you as an image because gamma scan. Now here you can see that in some places you can see dark spots, which is nothing but cancer. And why you are getting dark spots? Because from that particular position, lot of activity is coming out of the body because these are the cancerous lesions. They have FDG with significantly higher extent than the other normal cell. You can see the other part of the body is dull gray, whereas it is black. I hope you understood this scan. Now, before moving further, let me ask you one question. Here also you can see a very dark spot. Is it cancer? And the answer is no. It is actually our brain. And you know that brain is one organ which has highest amount of glucose. So naturally it will take up a lot of 18 fluorine FDG as well. And this is one of the limitation of 18 fluorine FDG. Because brain is having an inherent to take up glucose, if a patient is having a brain, then we will miss it because brain is already taking up a lot of fluorine labeled glucose. so we'll not be able to see that tumor residing in brain. Now, just like I told you, many buses going to different destinations, we have different radiopharmaceuticals for different applications. This is not an exhaustive list of radiopharmaceuticals, but just to give an idea that we have different radiopharmaceuticals for different type of applications. So before moving further, I would just like to request whether I am audible properly or it's everything is fine.
Yes, yes.
Yeah, thank you so much. Thank you so much. Thank you so much.
Thank you so much. Thank you so much.
Yes, yes.
Yeah, so we will move further. Cancer therapy using radiopharmaceuticals. So far, I have shown you one example of how we evaluate functional status of thyroid with the example of iodine. And then I showed you with the help of FDG, making glucose, how we can diagnose. And now I'll just touch upon how we use radiopharmaceuticals for therapeutic purpose. So essentially, what is cancer therapy? Cancer therapy essentially means we want to kill cancer cells. It's basically that. Now, if you look at cell, it has many important components, like it has a nucleus inside the nucleus, it has a DNA, which is very, very important biological molecule. Apart from that, in cytoplasm, it has so many important molecules like mitochondria and ribosomes and many other things. So essentially, our idea is somehow you deposit a lot of energy inside the cell and then permanently damage these vital molecules required for the survival of the cell, and the cancer cell dies. That is the logic. But the thing is, how do we do that? Now we ask the question, what is better for therapy? We know that gamma radiation is used for diagnosis because it has high penetrating power. But what is the intention in therapy? We are going to analyze that. So gamma radiations are basically massless and chargeless. Beta radiations are electrons basically, so they have light mass and one minus charge. And alpha radiations are heavier. They are basically helium nuclei with two positive charges. This information we are analyzing. Let us assume that these three radiations are passing through matter or tissue, body tissue. Gamma, because they are massless and chargeless, interact less with the matter. It's quite easy to understand that. Since they interact less, they loses less energy per unit length, and that is the reason they are able to travel long ranges because they lose energy less. So they can travel long. Beta particle, on the other hand, it shows moderate interactions because it has a light mass and one negative charge, so it can interact electrostatically as well. In the process, loses moderate to high energy per unit length, and therefore it is lower than what gamma does. Now go ahead, alpha particle that's having very strong interaction because two positive charges and is heavier. So it loses significant high energy per unit length and travels the least. And here I would like to introduce one more term called linear energy transfer. Very important term. Linear energy transfer means energy lost per unit length it travels. And if we look at the linear energy transfer of different radiations, alpha will be having the highest linear energy transfer. Why? Because it interacts strongly, followed by beta, and followed by radiation. And that is the reason why alpha or beta radiations are preferred. I call them radiation, they are actually particulate radiations. Alpha or beta radiations are preferred over gamma radiations for therapy. All right, fine. Now, how do they interact? You essentially, this is the basic of a cell. Now, these radiations interact in two ways. One is called direct effect. Here, what happens is that the radiation directly interacts with the macromolecules like DNA inside the nucleus, or mitochondria, or ribosomes, or whatever. And The second option is you must be aware that 80% of the cell is water. So it is very much possible that the radiation can interact with the majority component that is water. And the resulting effect is called indirect. Now, what is direct route? As I mentioned already, radiation comes and interacts with the molecule directly. Here I have just shown the DNA, but it can happen with ribosomes as well as other macromolecules inside the cell. And once it interacts, it can break the bonds. In the case of DNA, we say single strand break, double strand break. There are so many other reactions possible. But essentially, what I want to tell you is that this direct interaction process damages this molecule to such an extent that cell will find it really difficult to survive and it leads to death. And in indirect route virus, as I mentioned already, this ionizing radiations interact with water, deposit a lot of energy, and it results in breaking up of water molecules. It is called pyrolysis of water. And in the process results in the formation of very reactive hydrogen radical, OH radical, aqueous electrons, so on and so forth. And these reactive radicals and ions can carry out further damage to DNA or other macromolecules inside the cell. And what is the end result? Macromolecules are damaged, cell will find it really difficult to survive, leading to cell death. Either way, whether it is direct or indirect, ultimate aim is to kill the cell. Now I'll go to real life examples and just tell you how this works. First, again, I will take the example of thyroid cancer therapy. So thyroid is having a problem. There is an abnormal growth in thyroid and we want to treat it. So we already know that iodine knows its way to thyroid. And for diagnostic purpose, what we did, we had small doses, 50 to 100 microcuries of iodine, because our intention was just to diagnose the problem. Once we diagnosed the problem, we understood that, okay, this patient has a thyroid which is very cancerous, and now we want to treat it. Naturally, to treat it, we need to give more radiation dose, so it will be killed. So again, if you look at the nuclear characteristics of 131 iodine, it has a gamma, which we used for diagnosis. But here, we are going to utilize the beta radiation. There are actually two beta radiations, 131 iodine, 666 keV and 334 keV. And these beta radiations can be used to deposit huge amount of energy in this thyroid cancer cells and kill the cells. So what we do here, for therapy purposes, we increase the dose of sodium iodide, that is 131 iodide. We give 50 to 80 millicurie of sodium iodide to the patient. The patient will take it. Suddenly, it will start expressing more somatostatin receptors. So we say that there is an overexpression of somatostatin receptors when the neuroendocrine cell become cancerous. Now we are going to take advantage of this situation. Now we can design certain molecules which will go and bind to this receptor. Which receptor? Somatostatin receptor. And one of the many such molecule is dotatate. Don't worry about the name and all. This is dotatate. So dotatate is a small peptide which goes and binds to somatostatin receptors. So we have designed that molecule. So that will function as our bus. Now what I have to do is to follow some simple radiochemistry and then attach a therapeutic radioisotope. Our idea is for therapy. So I will attach a therapeutic radioisotopes such as 177 lutetium or 93. These are beta emitting radioisotopes. Once you make this, again, this lutetium-188, yttrium-188, it undergoes several cycles of voluntary control check since it has to be injected in a human patient. And after that, the patient having neuroendocrine cancers will be injected with required amount of mutation protein. Now, how much amount has to be injected, that varies from patient to patient, and that depends on the tumor load. Tumor load means how aggressive and how
Vadva sir. Hello. Hello.
Vadva sir नाही का?
Vadva sir.
Vadva sir नाही का?
हा सर. सर लेफ्ट झाले दिसत आहेत. हॅलो भागवत सर.
हा बोला.
आहे सर आहे.
मालिया सर.
आहे सर.
त्यांचा कनेक्शन गेला का?
मालिया सर लेफ्ट झाले. हा लेफ्ट झाले.
हो त्यांचं लेफ्ट झाले. लेफ्ट झाले. Connection.
No, Gaikwad sir. It is because of the problem with
connection, internet connection.
Connection at Anshakti Nagar.
Yes, definitely. That is problem.
Correct. Sir,
Bhagwat sir, can we proceed?
Proceed जाऊया.
हा आता आपल्याला कल्पना नाही. हॅलो, when he returns, we can give him the floor again.
Yes, definitely. Vadva sir, continue.
Yes, sir. I will request Shalini Misra to give vote of thanks for Malvi sir. Shalini Misra, please.
माइक बंद करा.
वधवा सर. भागवत बोलतोय. हा, त्यांना वोट ऑफ थँक्स इतक्यात देऊ नका. हा, पुढचा कार्यक्रम चालू करा.
No problem.
See, his lecture is not complete. So let us wait for.
परत मग सर डिस्टर्ब होईल ना. Disturb will
we will give it at the end. We will give vote of thanks at the end.
Okay. So I will request our faculty, Dr. L.V. Gowli sir, to introduce next speaker. Please, Dr. Gowli sir.
Yes, sir. On the occasion of World Nuclear Energy Day, 2nd December 2020, Department of Chemistry, Bhaurao Patil College, Vashi, Navi Mumbai Science Foundation in association with the Atomic Energy Regulatory Board and Indian Association for Radiation Protection under Deputy Star College status, organized online Enrico Fermi Memorial Lecture Series. It's my great pleasure to introduce today's speaker, Dr. Avinash Uddhav Sonole, a great eminent personality in the field of atomic energy. Dr. Sonole is acting as a head of the Directorate of the Regulatory Affairs and Communications of the Atomic Energy Regulatory Board and Secretary to the board. Sir has experience of more than 30 years in the safety regulations of ionizing radiation sources in the multifarious applications of the societal benefits. He is a recipient of Gold Medal of Indian Nuclear Society for his outstanding contribution in establishing a regulatory framework for ensuring safe usage of radiation sources. He is the national point of the contact in the International Atomic Energy Agency, WINEA, for the safety and the security of radiation sources. Sir, I welcome you on the above Department of Chemistry and Organizing Committee. Now I request you, please deliver this lecture on safety regulations of nuclear and radiation technology in India. Sir, please.
Presentation. Hello. Good afternoon, and all the delegates. Let me express my sincere thanks to Navi Mumbai Science Foundation and the Department of Chemistry of Karmaveer Patil College, Vashi, Navi Mumbai, for organizing this event and giving me an opportunity to share information on how the nuclear facilities and the radiation facilities in our country are regulated to ensure that they are safe and environmentally clean as such. I am just downloading my presentation, so please just wait for a minute. Yeah, right. Yeah. Am I audible, Dr. Bhagwan? Dr. Guy?
Yes, sir.
Yes.
You are audible.
Thank you. I'm just uploading the presentation.
Okay, sir.
नहीं मतलब ये तो आ रहा है It's okay. Yeah. Once again, I thank the organizers for giving me this opportunity to share some information about the safety regulation of nuclear and radiation technology in India. I know that we are very much lagging behind the time, almost more than 1 hour. We are behind the schedule. And there is definitely a pressure on the participants as well as on organizers that how to complete this in time. And I think this is sometimes the disadvantage of virtual meeting where the connectivity issues and then loading the presentation also make some issues. I think I may have to skip many slides because Dr. Jagtap has given a very good oversight over these low photon energies, and so is the important nuclear part. Some slides I will be skipping, and then the previous speaker spoke about the detection of a cancer by radiation. So those slides also I'll be skipping. So. You see, this ionizing radiation, what is ionizing radiation? I will not be explaining much as such, but since several students are there in the program, I will only like to say that we come across different type of radiations in our life, like, visible light, infrared radiation, ultraviolet radiation, radiation from the mobile, and so on. But today, what is the important thing, what we are dealing with is nuclear or ionizing radiation, which is emitted either by the radioactive substances like a cobalt-60, iridium-192, cesium-137, which are in fact produced in the research nuclear reactors like Dhruva in Bhabha Atomic Research Center. And this ionizing radiation is also emitted by applying the electricity, like, some sort of a very special devised equipment which generates the ionizing radiation. A very common example is the medical X-ray machines, then CT scan equipments, then radiotherapy machines, dental X-ray equipment. These all are the sources of ionizing radiation. We call it as atomic radiation or we call it as a nuclear radiation, but it is the same. And the difference between this ionizing radiation and other radiation is that this is a penetrating radiation. When it penetrates into the material, it may be the steel, it may be the paper, it may be the wall, it may be the biological matter like a human body. It produces the ion pair, that is positive ion and negative ion. And then we take advantage of this ionization process for the benefits of or the social uses of the radiation as such. So if you ask me whether this ionizing radiation is only man-made, is only produced by the man, or it exists everywhere. Yes, it exists everywhere. It is a natural radiation which is present everywhere. It is omnipresent. We are living in the ocean of the radiation, and it comes from the background radiation, starting from the formation of the earth. It is a part of the nature. It has always been there, and people have always lived with it. You are sitting in your house, in the auditorium, or in any room where you are sitting and viewing this webinar or viewing this program. You all are subject to the radiation, which may be from the radon, that is from the floor of the where you are sitting. It may be from the soil and rocks. It is from the plants like carbon-14. Our own human body emits the radiation like potassium-40 and the cosmic rays which are coming from the sun. So this is called as a naturally occurring ionizing radiation sources, which we cannot control as far as they're reaching to the earth, or they're which cannot utilize it properly or efficiently for the societal benefits. But then, so this is a naturally occurring radiation. We have to live with it. And another important is a man-made radiation, as I said, which is ionizing radiation source, either which is produced in the reactor or which is electrically generated. So these applications of man-made atomic energy are in various sectors. It ranges from the generation of the electricity to the healthcare sector, food preservation, hygienization, industrial applications, environmental cleaning. Various technologies are there, and national security like X-ray equipments at the airport also. So it's a wide gamut of applications of ionizing radiation for the societal benefits. And these applications are phenomenally increasing in the country all over, and of course, all over the world too. And if I have to speak about the applications of ionizing radiation in the healthcare sector, as I said, ionizing radiation, it can be again from the radioactive material which is produced in the nuclear reactor, or it is electrically generated like a X-ray equipment. So this is mainly used for the three important areas. One is the diagnosis. You know that it's very common that how we X-rays are playing important role in diagnosis of diseases. It's like in accidental case, like a fracture, or sometimes you have to see the location or depth of the tumor in the body, its size in the body. So many size of the tumor in the body. So there are many such diagnoses are there which are being carried out by ionizing radiation, like X-rays. Then another is a treatment, like the previous speaker, Dr. Madhav, has said that for the cancer treatment, it is for the whether it is a malignancy or whether it is iodine 131 for the thyroid cancer. So treatment of the cancer. Similarly, another is sterilization. So in the hospital, you may be knowing that single-use disposable products are being used, like tutors. Then similarly, the sterilization of the important, some sort of implants in the body, they require a 0% microbial load. So 100% sterilization is ensured by the radiation. So in the healthcare sector, so diagnosis, treatment, and sterilization are the important parts. This, I will not go much detail into that, but you see this picture, these are very common. Even a small clinic has a X-ray equipment. So means where the ionizing radiation is produced, that is X-ray is produced, and then it is used for the human body imaging, for the proper diagnosis, and then for further treatment. So how it contributes in some sort of enhancing the the quality of the life and or curing the patient as such. Similarly, computer tomography is one of the very, very common use of the computer tomography equipments, and they are very much in advance. Almost 40% diagnosis in healthcare sector is done by the CT equipment, and useful in obtaining precise human body images, detection of a cardiovascular diseases, and cancer treatment planning. I will not go detail much into that. My intention of showing this slide to you is that ionizing radiation is such important, such a beneficial, one has to really respect its benefits to the humankind. Similarly, the cath lab, you see the several interventional procedures are being carried out in the cath labs or in operation theater. It may be angioplasty, it may be angiography, it may be the TIPS procedure, it may be fistula procedures. So catheter is inserted into the body, and then we see that the cardiovascular, the system veins are properly, ensuring that the proper blood flow is there as such. So one has to insert the stent into that, whether the stent inside the body is going or inside the artery is going properly or not. When the patient has to be all the time in the X-ray beam, and then through the X-ray beam, we see the movement of the stent and we see the treatment as such. Such an important application of the cath lab, like a C-arm equipment, where the orthopedic surgery cannot be carried out without the C-arm equipment. C-arm equipment is again an X-ray equipment of a C-shaped with a X-ray detector and X-ray source, which is being used extensively. Now, another important application is a nuclear medicine, where we call it as a molecular imaging or a functional imaging. Whatever the imaging you have seen with the X-ray or CT, it is a static imaging. By nuclear medicine, one can see that here the radiopharmaceutical, again, which is prepared, in fact, in the Vashi itself, the complex of the board, that is a board of radiation and isotope technology, which is a unit of Department of Atomic Energy, where the radiopharmaceuticals such as technetium-99, iodine-131, thallium-201, fluorine-18 are used for diagnosis and treatment. Here, the patient is injected with the injection with this radiopharmaceutical. It spreads into the body, it gets accumulated into the sensitive organ, and then one can see the details about the behavior of the organ inside the body, and hence it is a diagnosis and treatment as such. So nuclear medicine is one of the very important application in the healthcare sector of radiation. So these are the different organs. One can study the details of the organs like a brain, kidney, lungs, spleen, liver, and so on, for any abnormality. And the radiation load received by the patient is, of course, the smaller than that in CT. Let me tell you, whatever the application of ionizing radiation is there, no doubt they are beneficial, but at the same time, they do carry some sort of a additional risk or the hazard to the body, but it should always be less than what the benefit the patient gets from such an application. So radiation therapy, I will like to skip this because the previous speaker, Dr. Madhav, has already explained that how effectively the radiation therapy is used for treatment of the cancer, where the patients, that the malignancy tumor or the lump where the that the carcinogenesis tumor is there. So it is bombarded with the gamma radiation, or it is bombarded with the X-ray radiation. As I said, it is again the atomic radiation, and the growth of the cancer cell is immediately reduced significantly, or it gets totally stopped. So radiation plays role in inhibiting the proliferation, the growth of the cancer cells in the body as such. So this is the external beam therapy, and we have developed the indigenous Babatron equipment in BRC has developed this Babatron equipment, and it is being extensively all over the country. And in fact, we have even exported these units to the countries like Vietnam and Mongolia as such for the treatment of the cancer patients. Another application of radiation is a brachytherapy, where the treatment of a cancer by placing radiation source very near to the lesion, like a breast cancer, cervical cancers, cheek cancers. They are treated with radioactive material called as iridium-192. This is implanted or inserted into the tumor, and then tumor gets exposed to the ionizing radiation, and that is how the growth of the cancerous tumor is controlled as such. So these are some important applications of radiation in healthcare sectors. There are many such applications, but because of the constraint of the time, I apologize that I could only project the major applications. Another sector, if you say radiation application in industry, this is the radiation sterilization of healthcare products, then sludge hygienization, radiation processing of food and allied products, and then blood irradiation as such. So sterilization, this is the gamma radiation used for sterilization of healthcare products on industrial scale. These products, as I said earlier, that they are single-use disposable products, and almost more than 60% single-use disposable products are being used in the healthcare sector, and they are sterilized only by gamma radiation. Of course, there are conventional sterilization products like ethylene dioxide one can use, or some fumigation one can use, but the assurance for 100% sterilization comes only with the gamma radiation. And these products like surgical dressings, ointments, latex flows, Ayurvedic medicines, orthopedic implants, pharmaceutical raw materials, these are being irradiated for sterilization, for ensuring the sterilization. And Isomed is the first plant in the country which was commissioned, I think, in 1974 in DRC. And today we have almost 22 such plants operating all over the country, and 2 are already operating in Vashi. So this is the radiation processing, another application for the cross-linking of polymers in the cable industries to enhance the quality of the cables, to enhance the durability of the cables, which are mainly used in very critical and sensitive areas like aircraft industry, the lifts, and so on as such. This is one of the important applications, that is Swachhata Bharat, that the radiation has played a role in contributing the Swachhata Bharat mission, where the very high activity cobalt-60 source, again, which is produced either by using the nuclear power plants or in the research reactor, and these sources are used for sludge hygienization plant. First was in Baroda, with the Baroda Municipal Corporation has installed this plant, and now recently even in Ahmedabad also it has started. So it processes tons of, in fact, the sludge which is collected by the municipal corporation, and then it gets allowed to pass through the cobalt-60 source, where the pathogens load is drastically reduced, and it can make a pathogen-free manure, which is used extensively by the farmers as a fertilizer. Then radiation processing of foods. As I said, the 2 plants are already in Vashi, 1 plant is in Nasik, and as I said, several plants are being operating in the country, where it is used for the quarantine of the fruits, spices and fresh foods, then chicken, meat and fish for shelf life extension, similarly insect inspection and sprout inhibition. So these are the plants which are, that like a radiation processing plant, Navi Mumbai, Vashi, which is installed at sector 20, then Kushak, Lasalgaon, Nasik, and several such plants are there, as I said. This is the picture I wanted to show, that the first consignment of the radiation processed mango, Alfonso mango, when it was exported to the US, even we continue exporting the irradiated mangoes to US, tons of mangoes to US every year. The picture you see, the FDA inspector from the US, he is examining the quality of the radiation processed mango, and then our team, our former chairman, Professor Banerjee, as well as our colleagues who have developed this technology. So another important is you perform using the cesium for the cesium-137 or cobalt source in a self-contained blood irradiation to prevent that TAGVT by inactive lymphocytes. You know that there are some suppressed patients are there, and before transfusion of the blood to the patient, like brain transplantation patients, then this blood needs to be irradiated so that the T lymphocyte is killed and the patient becomes, little bit immunoresistive as such. So this is one of the very important application. Then radiographic testing. Like X-rays are used for the human imaging, similarly the X-rays or gamma rays are used for the imaging of the industrial products, engineering products like a castings and weldings, to see that there is no any defect like a crack, porosity or lack of fusion or presence of some impurity, so that the quality of the engineering projects or engineering structures are ensured where they use the gamma source. This is the picture where the aircraft engine is being tested for the circumferential circular circumference. You see that it has been welded, and now the welding quality is inspected, because this is subjected to the high pressure, high heat, and it should not break, or there should not be any some sort of a damage to the welding. And then this can be only ensured by using the industrial radiography using X-rays or gamma rays. Then there are the nucleonic control systems, which are being extensively used for online measurement of the parameters like, the thickness, level, density, and coating gauges. And several thousand industries are using these instruments. They are called the nucleonic control systems. They use a very low activity reactive material for measuring, online measuring of these parameters as such. The picture which I have shown nearby is one of the moisture gauge, which is being used for when some flyovers or the concrete roads or the road structure is constructed or built, then to see that there is no void or there is no moisture gap inside the concrete thickness. So this is measured online with a non-contact by these nucleonic control systems. So these are some gauges, like this is a picture in the blue picture you see there where the density is online measured with the CGM source, while the right side picture of mine is where the brewery industries, where the thousands of cans are scanned for the proper filling of the liquor inside the can as such. It can be only seen by the radiation detection as such. And in the research applications, in the education, research and calibration purposes, unsealed sources, liquid sources are being used, and of course they are of a low hazard. And there are some pictures like cobalt-60 used as a source for mass-band spectrometry in the IITs and then postgraduate engineering and science colleges. Then cobalt-60 as a gamma source, then the cesium as a gamma reference source, neutron sources for studying, locating, and identifying of the light elements like low-Z materials, neutron diffraction to study atomic magnetic structure, inelastic scattering studies for study of atomic vibrations and other excitations. They are very interesting, applications of radiation even in the research as such. And other applications, these are called as the consumer product, like inspection of a baggage by X-rays, then whole body human scanning, mainly in the prisons and the security, the areas where there is a security threat, that whole body scanners are, gas mantles, lamp starters, and so on. Now, if I have to, so this is what I have explained about the applications of radiation for societal benefits in the various applications, in the various fields as such. Next application is the generation of electricity. As you know, that you may be knowing that we have 22 nuclear power plants which are generating the huge amount of electricity, and 11 nuclear power plants under construction. You may be familiar with the Tarapur plant, which is very nearby. And this is some sort of a picture where, like Tarapur site, where that so many nuclear power plants are being built. Then Kalpakkam site in Chennai, then Narora, Delhi, near Delhi. Then this is Kakrapara near Goa. Then Kakrapara near Surat, then Kaiga near Goa, and then Rawatbhata, Kota near Kota, and Kudungulum in Chennai. So these are the, overall the total 22 nuclear power plants, 11 plants are under construction as such. So since you may be knowing now that, there is a tremendous, very significant, phenomenal benefits of radiation and nuclear technology is there for the welfare of the people of our country, and hence this involves the huge transportation of radioactive material from one place to another place. In fact, every day thousands of radioactive packages of radioactive material are shipped and delivered around the world. Wherever PET CT is there the fluorinating source is there, it has to be delivered so speedily and safely. So 70% is just the medical isotopes which are being transported from one place to another place for saving the life of several thousand people all over the world as such. And but one has to remember in mind that even though there are appreciable, remarkable benefits of radiation, but one should keep it in mind that the radiation, ionizing radiation, years ARB has developed a mature and very robust regulatory process. ARB has established effective regulatory framework for governing control over radiation sources to ensure safety in their usages. However, the prime responsibility definitely lies with the operating organization or licensing. As far as the nuclear power plant are concerned, I would like to conclude that because of the potential of a very high consequences, the nuclear reactors are designed, built, and operated with highest standards of safety, due to which the probability of accident becomes very remote. And even if no probable accident occurs, there are measures to limit the progression and mitigate the consequences. That is in the next lecture, we will be hearing more. And ARB's regulatory supervision ensures that nuclear plants and radiation facilities are not only designed to take care of the worst possible accidents, but are also capable to tackle and mitigate the consequences of accidents. And this is my last slide, the message from AERB, that AERB appeals to participants of this program for spreading awareness on societal benefits of nuclear and radiation technology and safety regulations, oversight of Atomic Energy Regulatory Board. For further details, you may visit our website, that is www.arb.gov.in. So thank you very much. And also I would like to mention that there are good career opportunities in the field of nuclear technology. You can visit the sites of the Department of Atomic Energy, Bhabha Atomic Research Center, and Atomic Energy Regulatory Board, where there are the good opportunities for serving to this department. Thank you for patient listening. Thank you for the organizers for this opportunity.
I request our student Pratibha Devgare to give vote of thanks. Pratibha, please.
Good afternoon, everyone present here. I am Pratibha Devgare, student.
Yes, sir.
One more lecture is there.
Sir, after this lecture, I have arranged vote of thanks for each lecture, sir.
Okay.
Yes, Pratibha, go on.
Good afternoon, everyone present here. I am Pratibha Devgare, student of TY BSc Chemistry. It gives me an immense pleasure to deliver the vote of thanks for this event on Nuclear Energy Day. Today, my words are not enough to express the gratitude. So, on behalf of our reputed college, Karmaveer, Bhaurao, Patil, Vashi, I would like to thank our chief guest, Dr. Avinash Sonavne sir, who honored this function with their inspirational thoughts on safety regulation of nuclear and radiation technology in India. Sir, again, I would like to thank you for taking time out of your busy schedule. Thank you so much, sir.
Thank you, Pratibha. I request Dr. R.D. Mohite sir to introduce, please, Dr. S. Murli. Please, Mohite sir. Dr. Mohite sir.
Thank you, sir. Wadhwa sir, am I audible?
Yes, sir. Yes, sir. Yes, sir.
So, good afternoon to all the participants and all the team of the World Nuclear Energy Day. I am Professor Dr. Mohite. I am very happy to introduce the today's speaker, Dr. Seshadri Murli, Scientific Officer H and Head Emergency Preparedness and Response Section, Radiation Safety System Division, Bhabha Atomic Research Center. Dr. Murli sir has awarded Meritorious Operational Health Physicist in 2012 for his immense contribution in the field of radiological safety at nuclear facilities by Indian Association for Radiation Protection, IARP. He has received few awards from DAE for his contribution in the field of radiation safety and emergency preparedness. Dr. Murli sir has over 35 years of experience in radiation safety, radiation emergency preparedness and response. He is the honorary secretary of IARP and co-sponsor of this program. Dr. Murli has participated and delivered lectures at Fermi Day events for the past few years. Today's topic of his is the regulatory aspects of atomic energy. May I request Dr. Murli sir, please deliver your talk. Thank you, sir.
Thanks for the organizers for giving opportunity to speak on behalf of IARP's participation in this World Nuclear Energy Program Day conducted by Modern College, which has been a regular affair. And am I audible?
Murli sir, continue please. Hello. Hello. Murli sir, you are
Yes,
not
sir.
audible.
Yes, sir. I have given the thanks.
Murli sir, you are not audible.
Yeah, good afternoon. Is it audible now?
Murli sir, speak please.
It is very faint,
Hello.
sir. It is very faint.
Yes. Yes, it is looking good. Yes, screen is sharing.
Yeah. Good afternoon, and on behalf of IARP, Indian Association for Radiation Protection, in this World Nuclear Energy Day program, which is being periodically conducted at Modern College, and this presentation on regulatory aspects of nuclear energy program in India is, of course, some idea was thrown by my earlier speaker. So I'll be speaking about initially to give idea on IARP. It is a non-government organization which is little over 50 years, and then nearly 1,500 members are there who are from scientific, academic, like even college, university professors, students, research personnel, and we have around 500 persons, experts who are still serving and retired, dedicating their efforts on scientific, say, radiation safety and spread of gainful use of radiation technology. IARP is conducting core officers, as was mentioned by Dr. Sonavane, which is a requisite for players to have radiation technology used. So RSO courses are conducted by IARP, which is certified by Atomic Energy Regulatory Board. So this gives a job opportunity for those who want to have gainful use of radiation technology. IARP also conducts workshops, conferences, seminars, team meets in a periodic manner. We are publishing Journal of Radiation Protection and Environment, which is a quarterly journal in the field of radiation safety and environment. And we have awareness programs conducted for students and academic personnel on radiation safety in the Indian Nuclear Energy Program. And in Modern College also we have as the radiation safety expert, radiation emergency response director. Radiation emergency response director will be able to take the preemptive or the response actions which will minimize the impact of radiation emergency or to withdraw the countermeasures that are emergency response teams deployment. There are ESLs, environmental survey labs, across the operational facilities across India. So through his sort of chain, emergency response manager, emergency response team, and field deployment of emergency response team, receiving the information, we will be able to carry out the emergency response in a very quick and efficient manner. District Collector, Atomic Energy Regulatory Board, Crisis Management Group, and National Disaster Management Authority, wherein radiation and nuclear related events are also forming a part of their disaster management, emergency management, will be all in a parallel mode of operation, receiving the information and carrying out the response, carrying out the coordination among the response agencies, so that field deployment of be it DAE emergency response centers or the National Disaster Response Force, their emergency response personnel deploying will be carried out in parallel with the district and collectorate, district magistrate, who will be taking out the responsibility. And DAE is mandated to provide the technical support in providing the advice, in giving the support on the do's and don'ts on response mechanism. If required, DAE Emergency Response Center will be providing manpower as well as logistics for this response. We have got the plans and procedures right from the national level to the carrying out of crisis management group coordination to the incident where at locally nuclear facility or in the public domain any responses to be carried out. This sort of NDMA being brought in picture, crisis management group, Ministry of Home Affairs and the district and state level machinery being activated will carry out the response mechanism. We have got in BRC developed and tested for its efficiency during any emergency event usage, right from installed monitors to wide area coverage, aerial gamma monitoring, or compact aerial radiation monitoring device, or a quadrotor based or quickly deploying in case of any radiological emergency for a short area monitoring based on quadrotor. So we will be able to carry out a quick assessment of the affected site, suspected affected site by radiation monitoring, and then in case of personal movement, baggage, or any material crossing into the territory, we will be able to, and radioactive waste management can be carried out in an efficient manner. These monitors have been developed, and then Electronic Corporation of India Limited is provided the technical know-how for deploying at the strategic locations. Emergency response centers across India have been established. We have got, as on date, 25 such DAE emergency response centers, and we have provided the technical know-how and training for the NDRF to establish their NDRF emergency response centers at 12 different battalions locations, and DAE is likely to increase its battery of emergency response centers, additionally 6 locations. So we shortly will have across India closer to 40 emergency response centers, while presently we are having closer to about 35. The emergency response elements, key elements are, we are in support of our radiological emergency prevention and preparedness in case of any source which is not wound, orphan source we say, or the source which can create a threat perception, vulnerable source we say, or during the transportation from endpoint, from the generator to the endpoint user, if any accident takes place involving radioactive material or nuclear material, these could be potential scenario for radiological emergency, and this DAE is providing the technical know-how for response. Crisis Management Group, as I mentioned earlier, is the apex body for carrying out the coordination among the response agencies. We have 25 such emergency response centers operational. NPP, nuclear power plant, has got off-site emergency control their location for carrying out the response during the early phase. And we have got, for receipt of the information and coordination, 24/7 emergency control room with an alternate, both located at Mumbai. So we have emergency response teams with health physics experience, radiological safety, medical professional, fire and say other rescue personnel being trained, along with radioactive waste management, trained battery of personnel who will be able to provide response at any immediate requirement. So the response during any incident involves the category wise, we need to have the priority on saving human lives. The site needs to be made minimal so that control to that event site. The radiation levels has to be monitored. Thereby we will be able to affected site to less affected site to unaffected site. We will be able to segregate. Person need to be cleaned, contamination cleaned, that we call decontamination of personal area and equipments. We need to communicate to the public who are likely to be influenced, affected, or segregated, and then we need to have some measures on control of their intake, food, water, with alternate food supply and water supply regulated through civic administration. And these personnel who are evacuated needs to be relocated at a safer place. So response during any radiological event, we have scale-based event. We have a small 30-meter cordoning off to 400 meter to a kilometer, depending upon the scale of the event. First priority is life-saving action, just now as I mentioned. Background radiation level will be measured and we will be able to demarcate the area affected. And since we have got DAE emergency response centers at select locations, immediate our reaching may be slightly difficult. So NDRF, National Disaster Response Force, is also trained to provide emergency response in a quick time scale. We have crisis management group, which is coordinating along with other government agencies, including Ministry of Home Affairs, for carrying out response during any radiological event in the public domain. We carry out during any major event, be it Commonwealth game, during our say event, which is suspected event or investor meet event, we carry out the pre-meet sanitization of the area and hand over the area free from radiological aspects, so that the major event can be carried out without any hiccup. And we carry out a training of the law enforcing agency, so therefore they will be able to cater to any requirement on a short notice. Our personnel, DAE personnel, are training even defense and NDRF, thereby the human capacity in case of any emergency response, that is also addressed with the technical gadgets, procurement and supply in a periodic manner, it is ensured. This is what we have conducted the exercises to our defense and to the police personnel. Thereby, we in India, as on date, have got nearly 500 such courses being conducted, and even if we have sort of in each course some 20-30 persons who are still on active service, we should have closer to about 10,000 or so personnel who are trained in radiation emergency response. Thank you.
Thank you, sir. I request our student Varsha More to give vote of thanks. Please, Varsha More.
Dr. Vadma, sir.
Yes, sir.
Dr. Vadma, हे आपले डॉक्टर मालिया सर, मालिया हॅज कम बॅक, मालिया, तर त्यांना हे यांचा व्होट ऑफ थँक्स झाल्यानंतर हा त्यांना कंटिन्यू करायला सांगा.
चालेल ना, आलेत ना, हा. Yes, sir. More Varsha, please.
Hi. Yes, sir.
Varsha More.
Sir, I am Varsha Prakash More. Oh, yes, sir. I am Varsha Prakash More from KBP College in TY BSc Chemistry. On behalf of my college, I extend a really hearty vote of thanks to our chief guest, Dr. S. Murali sir. Today, we had an opportunity to hear your lecture of regulatory aspects of atomic energy program, and this will surely be going to our knowledge as to our future events. Thank you, sir.
So, as per suggestion from Dr. A. M. Bhagwat sir, I request Malve sir to deliver remaining their talk. Please, sir. Hello. Hello. Bhagwat sir, are you sir?
Yeah, I saw his name here. I saw his name. Is he? He should be in the audience. He should be in the audience.
Hi.
If you, I just आपण 1 minute announce करा पुन्हा. Otherwise, we proceed further.
Yes, sir. नाही दिसत आहे सर. नाही आहेत सर. काय करूया सर?
ते नाही का तिथे ऑडियन्स?
नाही
रिस्पॉन्स नाही.
नाही.
ओके. कारण त्यांचं नाव बघितलं मी वर कॉर्नरला येतं ना, त्यात त्यांचं नाव पुन्हा आलं होतं. Let us proceed. Let us proceed.
So we have conducted essay competition. As per part of essay competition, there are some winners, and from the suggestion from our HOD and principal sir, HOD Mr. Y. Gaikwad sir and in Principal Madam and Dr. M. Bhagwat sir, we every year the student who get rank in the essay competition, we can give them a 5 minutes to talk in front of dignitaries. So from this, I request Mr. Deepak Jha to deliver his essay, how he has written essay in the essay competition. So please, Deepak Jha, please Jha, deliver your essay, please.
Yes, sir. So I want
Deepak,
to share my screen, sir.
Karna, allowed it.
So now
पटकन कर रहे
it's visible.
हाँ
Yes. Okay, sir.
तुला जे शेअर करायचं ते कर.
Okay, sir. So good afternoon, everyone, respected professors and all my colleagues. I am Deepak Jha, a student of TYBSc Chemistry in Karmaveer Bhaurao Patil College. I am thankful to Wadhwa sir and all the professors of Chemistry department who give me a chance to speak. Today I am going to speak on the topic significance of saving energy. So, this is these are the some subtopics which are including when I am speaking. So the subtopics are: what is energy, various forms of energy, different type and different sources of energy, what is energy crisis, reasons behind energy crisis, methods of mitigating energy crisis, importance of energy in our life, and the conservation of energy and significance of saving energy. Let us proceed. So energy is defined as the ability to do work. We require energy for all type of activities. When we say a body has energy, it means that it is capable of doing work. When we look around ourselves, we will find countless examples where energy is used to do work. When an engine used to start from its fuel to move a car, that is a part of energy. A battery stores the energy needed to switch on the radio, mobiles, or any other gadgets. So now a question arises, what are the various forms of energy? In our daily life, we use different forms of energy, such as heat energy, light energy, mechanical energy, electrical energy, and so on. But the most common forms of energy are heat, light, and electricity. We use all these forms of energies for different types of works. As per requirement, one form of energy can be converted into another form of energy by using specific type of devices or processes. We get energy from our daily use from different sources. So there are two main different sources: renewable source of energy and non-renewable source of energy. Renewable source of energy are basically limitless energy source present in the nature. For example, the sun, the wind, the force of water, and the inner heat of the earth are the examples of renewable source of energy. We all know solar energy. Solar energy comes from the sun, reaches light and heat, and help us to and by the help of solar plates, we convert the solar energy into electrical or thermal energy as per our use. Just same as the wind energy and hydraulic energy. But the non-renewable source of energy like coal, these are limited source of energy on Earth. We use it as to generate electricity, but these are limited in today's world. So as the activities small or big, needed one or more another forms of energy. We can say that energy is the lifeline for our survival and development. Some Indian households, particularly in rural areas, goes without electricity for days. Even in urban areas, the situations is not very good. There are frequent electricity cut for several hours during a day. Recently, we also faced that situation when our electricity supply was cut off due to some technical issues. This became a severe problem during the summer. Energy demand in future uh, Energy demand in future will continues to increase as India's population and its needs continues to grow. So the situation in which electricity supply is decreased as compared to its demand is called energy crisis. Energy crisis is being faced by all developing nations, including India. So let me know what are the reasons behind energy crisis. It is a fact that presently around 85% of the world energy supply is made from oil, coal, and natural gas. Clearly, we live in the age of coal and oil, but the availability of both the resources of energy are very limited and will not last beyond a few decades. If we think about the India's situation only, coal accounts is 70% of the India's energy production. However, it is a limited resource and also creates environmental problem. Even if more coal is mined, the increasing gap between the demand and the supply of energy in India cannot be easily fulfilled. Indian villagers are forced to spend for 2 to 6 hours per day gathering fuel from their household cooking needs. Moreover, India relies on firewood and led to deforestation and pollution. So, thus, the basic reasons behind over energy crisis are our over dependence on limited and exhaustible source of energy, such as our coal and oil deposits, and the increasing gap in the demand and supply of energy, ever increasing prices of the energy and fuel from other countries, and the last one is overuse and misuse of the available source of energy. So, what are the methods of mitigating energy crisis? In order to mitigate the problem of energy crisis, the government as well as the people of our country should take collective and serious steps. It is believed that one possible solution to India's energy problem is nuclear power. Accordingly, we signed a nuclear deal to import fuel and technology. The model of nuclear power energy has been successful in countries like France, where they meet more than 75% of their electricity requirement from nuclear energy. The use of renewable sources of energy like solar power, wind power, hydroelectric power, biogas, and biofuel, etc., should be promoted. Being an agricultural nation, we could have come up with a more igneous solution, produce ethanol and biofuel for sugarcane and vegetable oils. So, what are the importance of energy in our life? Energy plays a very important role in our life, providing comfort, increasing productivity, and allowing us to live the way we want. Since the beginning of mankind, we have made use of wood, water, and the fossil fuels as a mean of heating and making machines work. Almost for all types of activities, we rely on one or another forms of energy. Amount of energy used by a society is an indicator of its economic growth and development. Without energy, even our body would not be able to perform basic functions like respiratory, circulatory, or digestive functions. Almost all the machines used for the production and manufacture of different types of items would be unable to operate without the use of source of electrical energy. Nowadays, electric energy has become so important that almost in all fields, electricity is required. For example, all electrical appliances in our homes and at our workplaces require electricity. All the industries and factories runs on electricity. So how do we conserve energy? The key for resolving the country's energy crisis lies with us citizens. Among things we can do is the conservation of our non-renewable sources of energy. It is said that energy saved is as good as energy generated. Therefore, we should not only jealously use energy source, but save energy as much as we can. We can save conservation of energy in our homes. Some of the important tips we also know that some of switch off the lights, fans, and other appliances when not in use. Water and the water tap should not be open left. While cooking rice or dal, the vessel should be remain covered that we can save our gas through this process. Another way of saving energy is by use of more efficient appliances. For example, LED, CFL light is more efficient than a tube light or bulb, etc. There are only some of the habits which can save a lot of energy. We should find way for not wasting energy where it can be saved. For example, if we are required to go to a near place, we may walk or go by a bicycle and avoid the use of automobiles. We may use public transport in place of our own vehicle to save fuels. Share automobiles, ride to offices, colleges, or any other places instead of driving alone. If we use more renewable energy instead of non-renewable energy, then the amount of these non-renewable energy will be maintained or will be available for long period of time. And the bad effect due to the overuse of non-renewable resources will be less and our environment will be clean. We have to learn something from Bhutan. Bhutan is the only carbon negative country in the world. That means absorbs more carbon than it emits. Bhutan is heavily investing its renewable energy like geothermal and hydropower plants. They are aiming to become a zero emission country by 2030. So this is one of the things which we have to learn from Bhutan. And by saying a last word, I am concluding my speech that as much as energy saved is as energy generated. Thank you.
Madhva sir? Madhva sir?
हॅलो आय रिक्वेस्ट हा सर बोला ना भागवत सर बोला ना
पुढे पुढे नाही नाही मला गॅप पडली
नाही मी म्यूट केलं ना मला तनुश्री शेवडे प्लीज तनुश्री शेवडे फ्रॉम FY-BSc एक्सप्लेन युअर एसे प्लीज तनुश्री आहे का
हो सर हो
प्लीज प्लीज एक्सप्लेन कर
Good afternoon to one and all present here, respected principal, guests, teachers, and all my dear friends. Myself, Tanushri, is here to speak on the topic which has very powerful impact on our living life, that is significance of saving energy. In this era, the energy is an essential component without which we cannot imagine living or performing any of the tasks. For the comfortable lifestyle, energy plays an important role. We perform various tasks with the energy, such as heating, cooking, lighting, etc. With the help of falling energy, we run our vehicles and move from here to there. With the coal and wood energy, we cook our food and keep our homes warm. Therefore, it seems obvious that how much useful the energy is for our life. All these facts and importance of energy makes us realize that if we will not have any energy around us, then life will be really difficult. With such importance, it is very crucial that we save energy as well as for our upcoming future needs. As we see that by saving energy, we can overcome many key issues on the earth. Many countries are facing pollution in various forms, like air pollution, water pollution, and land pollution. By saving energy, these issues can be eradicated. Since this law of conservation is held to be true, it means that it is up to humans to save energy in every possible way. All of us at a time in our life must have got scolding from for leaving our room without switching off light and fans. At that time, it might have occurred to us that parents screams at us because they have to pay a hefty electricity bill. Conservation of energy reduces pollution because it lower downs the number of resources that are put to use. This causes less of toxin being released into the air. In the end, however, it is also to be considered that the conservation of energy is all about human behavior. If human beings choose to behave irrationally and forget about the future, then neither is conservation possible nor is the future safe for the generation that are yet to come. As we all know, energy conservation plays an important role in saving non renewable resources. Energy conservation will reduce the expenses related to fossil fuel. Fossil fuels are very important to mine. Non renewable resources takes many centuries to generate. Moreover, human consumes energy at a faster rate than the rate of production. The air pollution due to fossil fuels can cause various respiratory problems. A nuclear waste can cause cancer and other deadly problems to health. World Nature Day is observed annually on 20th July to remind mankind about the importance of nature and need to protect it. Describing how nature worship was an integral part of Indian culture and how we should all take a pledge to protect, conserve, and sustainably manage our natural resources. Quote, there is no energy crisis, only a crisis of ignorance. So I would like to end my speech by saying a small poem. Be polite, turn off the light, conservation, not deprivation, conserve to preserve, do a earth a favor, be a power saver. Thank you.
हेलो
हो गया हो गया
एक स्पीकर अजून आहे ना? मध्वा सर, मध्वा सर, गायकवाड सर,
He's not there, I think.
one of them, I know they are cut off. I think they will be there.
They will be there means online. Yes,
there is some problem, that means.
Yeah.
Because we have to wait. See, once one essay is to be read, and then they are proposing vote of thanks, no, for the whole event. Madhva sir?
Sir, I should start with my essay.
There is one. What happened to Madhva sir?
No.
Okay.
She can start.
Who is the third speaker? Essay? Third. Who is the individual?
What is the name?
Please go ahead. Please go ahead.
Thank you, sir. Myself, Tanuja Pawar, and I'm going to speak on nuclear energy in perspective. Nuclear energy is energy in the core of an atom which is produced by nuclear fission. It generates baseload electricity with no output of carbon. Switching from coal to nuclear power is radically decarbonizing since it releases greenhouse gases only from the ancillary use of fossil fuels during their construction, fuel processing, maintenance, etc. Nuclear power plants operate at much higher capacity than renewable energy sources or fossil fuels. Capacity factors actually measures what percent of the time a power plant actually produces energy. It is a problem for all the intermittent energy sources as the sun doesn't always shine, nor the winds blow or water always flows through the turbines of a dam. Also, nuclear power releases less radiation into the environment than any other major energy source, unlike coal, which contains uranium and thorium.
Tanuja, carry on.
Yes, sir. Yes, sir. The next point is the nuclear accidents that occurred in the past, like the Chernobyl accident, in which almost 31 workers and indirectly 1,400 people died due to 131 iodine present in the milk of kids and adults, which caused blood cancer. While we listen to this number, we can note that nuclear energy accident causes very less death as compared to fossil fuels. As estimated, nuclear energy results in 99.8% fewer deaths than brown coal, 99.7% fewer than coal, 99.6% fewer than oil, and 97.5% fewer than gas. Even if we combine the total number of deaths caused in nuclear accidents, the total figure is still much lower than the death rate from fossil fuels. All the above mentioned point tells us how much nuclear energy is harmless alternative. We should also consider the point about how it decomposes, which I think is the most important issue to consider. Radioactive waste is a byproduct which is generated while decommissioning and dismantling nuclear reactors. These are these are two broad classifications of nuclear waste. First is high level waste and second is low level waste. High level waste is primarily spent fuel removed from reactors after producing electricity. Low-level waste comes from reactor operations. In this waste, 97% is low-level waste, which is typically stored on-site by licensees, either under either until it has decayed away and can be disposed of as ordinary trash, or until the accumulated amount becomes large enough to warrant shipment to a low-level disposal site. Unlike other industrial toxic wastes, the principal hazard associated with high-level waste diminishes with time. The safe, environmentally sound disposal of this waste is technologically proven with international scientific consensus on deep geological repositories. At least 25,000 shipments of high-level waste have been made worldwide. The primary assurance of safety in transport of nuclear materials is the way in which they are packaged. Packages that store waste during transport are designed to ensure shielding from radiation and containment of waste, even under the most extreme accident conditions. As we can see that nuclear energy brings up multiple sustainability advantage and is robust due to its energy density and internationalization of health and environment costs, an analysis of nuclear energy
एकच
characteristics
आठवण कर
of sustainable development framework.
ऑनरेरियम ते PNBचं अकाउंट द्यायचं. गुड.
An analysis of nuclear energy's characteristics with a sustainable development framework shows that the approach adopted within the nuclear energy sector is consistent with the central goal of sustainable development of passing a range of assets to future generation while minimizing environment impacts and burdens. So, hereby I would like to conclude my speech by saying that nuclear energy is the future of energy source.
Thank you, Tanuja. I request last essay contestant from this competition, Miss Sonali Bade. I request Sonali to explain her essay. Please, Sonali. Sonali, आहे का Bade?
Yes, sir.
Please, Sonali.
Good afternoon, sir. Myself, Sonali Suresh Bade from TYBSc, KPP College of Vashi. So, my topic name is nuclear power. Nuclear power is the use of nuclear reaction that release nuclear energy to generate heat, which mostly frequently is then used for steam turbine to produce electricity in the nuclear power plant. Nuclear power can be obtained from nuclear fusion decay, and nuclear fusion reaction. Presently, the vast majority of electricity from nuclear power is produced by nuclear fusion of uranium and plutonium. Nuclear decay processes are used to niche applications such as radioisotope, thermoelectric generators. Generating electricity from fusion power remains at the focus of international research. Nuclear power has one of the lowest level of fatality per unit of energy generated components to other energy sources. Coal, petroleum, natural gas, and hydroelectricity each have caused more fatalities per unit of energy due to air pollution, and hydroelectricity each have caused more fatalities per unit of energy due to air pollution and accidents. Since its commercialization in the 1970s, nuclear power has prevented about 1.84 million air pollution related deaths and emission of about 64 million tons of carbon dioxide equivalent that would have otherwise resulted from the burning of fossil fuels. Accidents in nuclear power plant include the Chernobyl disaster in the Soviet Union in 1986, Fukushima nuclear disaster in Japan 2011, and the more content 3 Mile Island accident in the United States in 1979. The first power station to produce electricity by using heat from the splitting of uranium atom began operating in the 1950s. Today, most people are aware from the important contribution nuclear energy makes in providing a significant proportion of a world's low carbon electricity. The application of nuclear technology outside in civil electricity production in power plant are less well known. A radioisotope, nuclear power process, heat, and non-stationary power reactor have essential user across multiple sectors, including consumers product, food and agriculture, industry, medicine, and scientific research. transport and water, resources and environment. India started at the 13th place worldwide in generating electricity from nuclear source and expects to increase the installed nuclear power capacity from 5,780 megawatt to 10,080 megawatt by 2019. The one of the best thermal power plant station in Maharashtra, Thermal the Chandrapura Super Thermal Power Station is a 2,920 megawatt power plant in Chandrapur, Maharashtra. Three reasons why we should continue using nuclear energy. The first reason is nuclear energy saves a life. In 2030, a study conducted by NASA found that nuclear energy has prevented around 1.8 million deaths. Even if you include the death tolls from Chernobyl and Fukushima, nuclear energy rank last in death per energy per produce. While nuclear waste is really toxic, it's usually stored somewhere while the toxic byproducts of fossil fuels are pumped into the air we breathe every day. So just by reducing the amount of fossil fuels burned, countless cause of cancer or lungs disease and the accidents in coal mines have been avoided. If we can choose between lots of dangerous stuff being put into a deep hole and lots of dangerous stuff being pumped into the atmosphere, the former seems more logical. Nuclear energy feels way more dangerous and though. The single the single catastrophic events burn into our memory while the coal and oil kill silently. It's like a death rate of flying versus driving. Even in the best case scenario, it would take at least 14 years to switch to 100% renewable energy. Energy.
हॅलो सोनाली झालं हॅलो सोनाली कनेक्शन पुअर आहे बाळा हॅलो हा कनेक्शन कमी आहे हा झालं पूर्ण तुझं
Sir, 2 points are remain.
बरं बोल पटकन
So second point is the nuclear energy reduce CO2. Nuclear energy is arguably way less harmful to the environment in terms of climate change than fossil fuels. Our main source of energy since 1976, about 64 gigawatt of greenhouse gas emission have not been pumped out thanks to nuclear energy. And by the mid 21st century, that could amount of an additional 80 to 2040 gigatons. Humanity energy consumes in rising steadily. According to its government projection, China alone will add the equivalent of new 600 megawatt coal plants every 10 days for the next 10 years. China already burns 4 billion tons of coal each year. Coal is cheap, relatively abundant, and easy to get it to. So it's not likely that humanity will stop using it soon. Nuclear energy might be a only way of dampening the effect of climate change and the preventing the catastrophic man-made global warming. Compared to the other things, we do a nuclear energy is relatively clean. So even if it is a good idea to quiet energy long term and might be a good solution for next 100 years or so compared to the alternate. The third and the last reason is new technology. Maybe a technology will solve the problem on nuclear waste and the dangerous power plant. The nuclear reactors we have used so far as mostly a dated technology because a nuclear innovation stopped in 1970s. There are models like the thorium reactors that could solve the problem altogether. Thorium is abundant, really hard to turn its nuclear weapons and up to 2 orders of magnitude less wasteful than current nuclear reactors. The waste material might also be only dangerous for a few hundred years in contrast of couple of thousand years. 1 ton of thorium is estimated to provide the some amount of energy and 2,000 tons of uranium or 3,000 million tons of acid. So save energy. Thank you so much, sir.
So I request Shivani Misra
Yes, sir.
vote of thanks for this session.
Yes, sir. Good afternoon, honorable dignitaries and all my respected teachers. I, Shivani Mishra from TYBSc, on behalf of Chemistry Department,
Propose a vote of thanks to all my classmates and juniors. Deepak Jha, Sonali Bade from TYBSC, and Tanuja Pawar and Tanushri Shevde from FYBSC have given a wonderful speech on this occasion. On the occasion of World Nuclear Day program, we have gained a new knowledge on various topics, which is very inspiring one. A warm thankful to all of you for your efforts and making this occasion memorable. Thank you.
Bhagwat sir, we are at the end of the program. At the end of the program. So can we propose vote of thanks or you have to say something?
Yes. नाही तुम्ही vote of thanks present करा सगळ्यांना सांगा म्हणजे right from Dr. Jagataap.
Yes sir, yes sir, I have that one.
Right.
Yes sir.
आणि प्रिन्सिपल मॅडमला पण थँक्स द्यायचे.
Yes sir, ते घेतो. Yes sir. Yes. तुम्हाला काय बोलायचं सर? तुम्हाला काय बोलायचं?
नाही आता काय? नाही.
Okay. So I am here to propose vote of thanks. From last couple of months, NMSF chairman Dr. A.M. Bhagwat sir and our chemistry department team is engaged to conduct this program. So for this program, we have our principal Dr. S.S. Nayak madam. I am thankful to Dr. S.S. Nayak madam on behalf of Department of Chemistry and NMSF. Then I am thankful to our resource person, Honorable Professor B.N. Jagtap sir, for giving nice lecture on Enrico Fermi as an Enrico Fermi memorial lecture. So I am thankful to Dr. B.M. Jagtap sir, behalf of Department of Chemistry, KBP College, Vashi, Navi Mumbai, and NMSF Mumbai. Beside that, I am thankful to Dr. Madhav Malia sir, who has given a wonderful lecture on radiation for cancer detection and cure. So I am thankful behalf of Department of Chemistry as well as NMSF Navi Mumbai. Then I am thankful to Dr. A.U. Sonone sir. Sir has given a very nice lecture on safety regulation of nuclear radiation technology in India. So I thank Dr. A.U. Sonone sir. Beside that, Dr. S. Murli sir giving a very nice information about regulatory aspects of atomic energy program in India. He has given a lot of regulations, what are the types of regulation and what we can go through this one. So I am thankful to Dr. S. Murli sir, behalf of Department of Chemistry, KBP College Vashi, and NMSF Navi Mumbai. Beside that, I am thankful to all colleges from Maharashtra and outside Maharashtra which are part of this competition, essay competition, general chemistry, science competition, as well as general chemistry quiz. Then I am thankful to all who are my friends, my colleagues, my departmental colleagues, and all college members and NMSF to give us this opportunity to conduct this type of good World Nuclear Day or World Energy Day. So I am thankful to one and all. So I thank all, and I think we are stop here. Thank you, sir. Thank you.
Vadwa sir, one sentence I want to add.
Yes, sir. Yes, sir. Yes.
On behalf of the organizers, I feel sorry for Dr. Madhav Malia that he could not complete his talk because of some technical difficulties. We hope that he will forgive us for that difficulty which he came.
Yes, sir. Yes, sir.
Yeah.
Yes.
Okay. Thank you.
So,
now you can stop.
Okay. By the permissions of all, we can stop here. Thank you one and all for your nice and graceful presence with us. Thank you. Thank you, sir. Thank you. Bhagwat sir, we can stop here, na? Bellary sir?
Yes, sir.
Yes, sir. Okay,
Thank you.
sir.
Thank you very
Okay,
much.
sir. Bellary. Thank you, sir. Thank you.
Thank you very much.
Thank you one
Bye.
and all. Thank you. Okay.